sister of Apollo. Artemis is the name given to the program that will return humanity to the moon, and named after one of the largest constellations in the sky. Orion is the spacecraft destined to get us there. Through Artemis missions, NASA will land the first woman and the first person of color on the lunar surface. And these missions will allow us to explore more of the moon than ever before, paving the way for long-term presence in lunar orbit.
We're rolling the Orion spacecraft out, but it's beginning its journey. We're really kind of at the end of the building process and the beginning of getting ready to go fly.
But before Orion can travel to our nearest celestial body, it must first make a few pit stops along the way to fuel up and get ready for flight.
As we leave here today, we're going to go to a facility that'll fuel the spacecraft with the rocket fuels and propellants it needs. We'll put a launch abort system on. We'll send it out to be stacked in the rocket and launched. And it's really the last few yards of the game.
Orion's journey to the moon began on the bayou. NASA's Michoud Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the O&C building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the O&C. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module, such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks. Once the structure is deemed strong enough, the crew module is moved just a few spaces down into the O&C's clean room for its next round of integrations.
We bring that structure into our clean room, which is you see behind me, because we need to start integrating the propulsion system and elements of the environmental control and life support subsystems, and those systems require a cleaner environment than the one we're standing in out here.
When all of that is done, the crew module is on the move again to the crew module integration station. There, all of the electrical systems, including wire harnesses and avionics boxes that control the crew module's guidance, navigation, communications, and its power subsystems, are integrated. Next, it's time to bring the spacecraft to life.
We power it up, and then we go into a whole series of functional tests to make sure all the subsystems that we've integrated up to that point are functioning properly.
But the crew module isn't the only thing that makes up the Orion spacecraft.
All the people, the work, the components that have gone into this vehicle, it's just an amazing feat.
teams also worked closely with the European Space Agency to build the service module, the element that will power Orion on its journey around the moon. Once that arrives, from Bremen, Germany, Lockheed moves forward with integrating the two.
The service module has a very similar life cycle to the crew module. We build it up structurally, we integrate the propulsion system and the other fluid systems, and then we integrate it electrically and power it up and do functional tests on it. And when we have a full service module and a full crew module, then we stack the two together and we have what's called the crew service module for Artemis 1.
Under the Artemis program, NASA plans to not only return to the moon, but to use that as a stepping stone to go farther than any human has ever gone before, Mars. To get there, it's truly a cross-country and international effort among thousands of individuals.
When you consider all the people, you know, at the Johnson Space Center, Marshall Space Flight Center, all across the agency, SLS, Orion, the European service module, Boeing and their team, Lockheed Martin and their team, and to see all of that come together on that launch when we send it on its way to the moon, it's going to be absolutely amazing, and we're going to have a lot of really proud, happy people.
Building a spacecraft destined for deep space exploration from the ground up is no easy task. And the fact that these teams have been able to come together and do just that in the midst of a global pandemic is nothing short of amazing.
You know, it really is a testament to the workforce. If you think about what we've been through over the years that they've been putting this together, and particularly think about the environment that this team was dealing with. We're dealing with COVID, and we're asking these folks to come into work every day and finish the spacecraft so we can keep this mission going. And we're ready, and we're excited. And so as they turn this over to us, we're ready to get going.
And really, this is only the start of Orion's path to the pad.
It's a little hard to put into words when you think about the fact that we are in the first flow of what will be our nation's deep space exploration program. It hits you in the heart, and it really speaks to why we all are doing what we're doing.
I never thought as a little kid growing up I'd be part of something like this today. Now as a dad of two young girls, to be able to tell them what I do and to be able to have them someday watch the first woman stand on the moon is pretty amazing to me personally.
As the Orion spacecraft departs the ONC, its next stop is the Multi-Payload Processing Facility, or MPPF, where teams with NASA's Exploration Ground Systems and prime contractor Jacobs will perform the next set of milestones, fueling and servicing the spacecraft.
We have a few months of hard but rewarding work ahead of us to get to launch, but this is it. This is our year. This is our time and what folks have worked so hard for.
Now, we're going to continue with processing, get that thing checked out, fueled, get the launch abort motor stuck on top of it.
With fueling of Orion's crew and service modules,
Thank you, sir. Now let's hear from our spacecraft directly.
All of us would contribute to writing songs, and the reason it was so important to us is because it was very cathartic to sit there and, figure out how to make our struggles into, some funny song parody.
Well, bless my soul, what's wrong with me? There's 3 of my ribs just can't pull free. The brackets got a little bit snug on them pins. I'm all hung up.
And so we ended up calling ourselves the Galileo Not Ready for Real-Time Players.
I flew past Earth and it felt so fine. Better than a ride in a bumpy truck with them pins.
It really was a great stress reliever because we made fun of everybody and everything.
But talk like that don't ease my mind. Gonna get some sun where the sun don't shine.
Our number one goal was to be as funny as we possibly could. Musicality was really a tertiary concern.
Despite Galileo's lack of a main antenna, the spacecraft was already making science history. The initial flyby of Earth also provided the first global portrait of our planet in motion.
So, after the first Earth gravity assist, we took an image with our camera every minute for 24 hours so we could make a first ever color movie of the Earth making a full rotation on its axis.
Images of the backside of our moon confirmed the presence of an enormous impact basin, a discovery that hinted of surprises to come. Next came the first ever encounter with an asteroid.
We don't know what an asteroid looks like. We have a lot of guesses. A lot of them are probably wrong.
So they were interesting bodies we didn't know much about, and we were flying right through there. Now, this scared the heck out of the engineers. Through the asteroid belt, that's got to be lots of dust there, and you're going to run into things. It turns out the asteroid belt in between where the asteroids are is fairly clean. But right around an asteroid where you want to fly if it's interesting, the asteroid has some gravity, and you might have a little dust cloud hanging around it.
The worry was real, for colliding with even a small particle might cause serious damage to the spacecraft. Galileo was kept a safe distance of 1,000 miles away as it flew by asteroid Gaspra and gave the world the first ever image of an asteroid. Next came the second flyby of Earth, followed by another asteroid encounter that came close to being called off.
As we were approaching Ida, I had the occasion to be on the graveyard shift, and as soon as I got into my seat, one of the temperature monitors went into alarms on one of the science instruments. Didn't know why. So I called Bill O'Neill, who came in, and I'll always remember this. He sat down to the conference room table and pulled out a jar of instant coffee and a bottle of Pepto-Bismol.
The temperature alarm was solved. But next, Galileo's inertial pointing mode, used to keep the spacecraft oriented in the right direction, malfunctioned. Not understanding the reason why, some team members saw more risk than benefit in recording measurements during the flyby. But not everyone.
I'll give it to you when it comes along.
We didn't know what the problem was, but we knew that we could do the flyby. We could still point the scan platform and all the instruments using just the star tracker. And the attitude control people are like, come on, we can do this.
Asteroid Ida turned out to be twice as large as Gaspra, stretching over 30 miles in length and estimated to be 1 billion years old. And scientists were delighted to discover a new first. Circling the asteroid was its own tiny moon. After leaving the asteroid belt behind, Galileo took part in an experiment to detect gravitational waves, ripples in the fabric of space-time predicted by Einstein. Nothing was seen, but the elusive waves would turn out to be very real when they were detected 21 years later. Next, out of the blue came an extraordinary opportunity. Because of its position, Galileo would have the only ringside seat to directly witness fragments of a comet colliding with Jupiter.
This is a totally new event. The first time in the history of civilization, we are seeing an impact of a comet into a planet. The importance of the Galileo mission, you just can't say too much about it. It is the only spacecraft that both has an operating camera and that is going to be able to see the impacts directly.
The comet, originally a mile wide, was torn into pieces by the force of Jupiter's gravity. And Now all those fragments were about to slam into the gas giant in a series of spectacular explosions. Over the course of 6 days, the fragments, one after another, plowed into Jupiter's southern hemisphere, exploding into massive fireballs, rising upwards more than 1,000 miles. The energy of one fragment alone was the equivalent of 6 million megatons of TNT, hundreds of times more powerful than the combined energy of all of the world's nuclear weapons.
My first thought was disbelief. This was such a complicated process. I thought the chances of actually capturing the right moment with enough information to actually record the energy coming from these things wasn't all that high. And I was just amazed at all this complicated planning and jiggling of times and this, that, and the other, and the things that had to go on to get the data back had actually worked. So I was just amazed.
Galileo's images were key to determining the force of the collisions, while the aftermath of the impacts was captured by the Hubble Space Telescope and Earth-based observatories. The Hubble images revealed vast dark blotches stretching across thousands of miles. It was a sobering reminder of the kind of cataclysmic violence that occurred during the early formation of the solar system, and that is still possible in our own time. Galileo was also carrying a passenger, a probe designed by NASA's Ames Research Center and built by Hughes Aircraft. The probe was designed to separate from the mothership 5 months before Galileo's arrival at Jupiter. It would then freefall for 50 million miles on what would have to be a precise and no second chance trajectory to reach Jupiter. If all went well with the navigation, the probe would then slam into the planet at over 100,000 miles per hour, the highest impact speed ever attempted by a human-made object. The angle of the entry had to be near perfect also. Too steep and the probe would be incinerated. Too shallow, it would bounce off Jupiter's atmosphere like a stone skipping across a cosmic pond. 2 minutes into descent, the probe's speed would be reduced to just 1,000 miles per hour, slow enough for a parachute to deploy. From this point on, the probe would attempt to determine Jupiter's chemical makeup, measure the planet's temperatures, winds, and atmospheric pressures, and listen for sounds of lightning. An hour later, having descended just 400 miles into an atmosphere 3,000 miles deep, the probe would be vaporized.
This is the first time we've ever gone and directly sampled the atmosphere of one of the outer gas giant planets. So the sort of information that we get from this probe mission is unprecedented. This is the most difficult atmospheric entry that's ever been attempted.
The release went off as planned. A set of springs gently pushed the probe away and towards Jupiter in the far distance. Whether on the right trajectory or not, no one would know until arrival day. Nor would there be any information about the probe's health. To save its battery, the probe would have to coast in deep sleep and radio silence. An internal timer would awaken the probe just before its jarring encounter. Despite the uncertainties, rather than fret on the eve of release, friends, family, and mission members gathered again in JPL's auditorium to learn the latest on the mission.
Okay, good evening. We're going to start the program now. I hope you guys in the back.
And to hear, as was by now the tradition, from the not ready for real-time players. Though still millions of miles away, Jupiter was already making its presence known. Galileo found itself plowing through an interplanetary dust storm. For weeks, the spacecraft was bombarded by thousands of electrically charged particles scientists thought must be coming from somewhere in the Jovian system. 2 months before arrival, Jupiter could be seen in the far distance, close enough for Galileo to take pictures of the planet to share with the world. As planned, the images were stored on the reel-to-reel tape recorder, but after sending a command to begin playback, the Galileo team was shocked to discover that the tape recorder had been stuck in rewind for 15 hours.
It was one of the darkest days on the project. There were resumes flying off the printers, and we just thought the mission's over. We couldn't get one picture back from Jupiter without a high-gain antenna and without a working tape recorder.
When we had built our primary mission now on this tape recorder, that had to be the low point. It was within a day or so that we determined that we hadn't, in fact, broken the tape, and we probably could recover it. And I think it was about a week before we actually moved it. But what a relief that was. Of course, we're delighted that the tape recorder is not broken. What we don't know is just how operable it is.
The engineers cleverly figured out that the lubricant on the tape may have just gotten sort of old and sticky, and if they, as the tape recorder is running forward, once it stopped, it would get sticky and it wouldn't be able to go forward again, but if they backed it up a little bit, they could then get it going again forward. So we had to redesign the way we were laying down our data on the tape, and we had to allow for that backup and forward motion. So we had a lot of challenges, but we managed to get through them.
Leslie Tampari joined the mission as a graduate student, pursuing a PhD about Jupiter's inner moon, Io. Because of Io's intense radiation, there would be only one chance to collect data there during the prime mission. But the tape recorder crisis put an end to those plans.
We must avoid any unnecessary use of that tape recorder until we record the probe data, because there's only one chance to do that. There's never another chance to get probe data after this essentially suicide mission of the probe into Jupiter. I made that decision without having a meeting of the project science group and asking them all for their input. Well, these were tough times, and the clock was running. And I didn't need a lot of discussion and a lot of their input, because the buck stops here, and this is what we're going to do.
So as a result of that, I lost my PhD thesis. And so then I had to start over from scratch.
Tampari would go on to earn her PhD, though the topic would be about Mars. Her experience was one more example of how engineers, scientists, and even a graduate student would have to adjust to Galileo's unexpected, but certain to occur, twists and turns. Jupiter is immense, a world large enough to contain more than 1,000 Earths. Yet it has the shortest day of all the planets, just 10 hours. This extreme rotation speed helps to explain Jupiter's complex and ever-moving tapestry of cloud bands and giant storms, as well as the planet's deadly radiation, a place where not even machines can survive for long.
We don't ever experience that here on Earth, except as the result of like a nuclear weapons explosion or a nuclear meltdown. It's created because particles come off of Io and get ionized and spun out by Jupiter's magnetic field, and so these very, very fast-moving ionized particles constitute radiation, and they're incredibly destructive to living tissue. They go through your body like a bullet. They're very hard on electronics, as we found out.
Galileo was now on final approach after a journey of 2.5 billion miles. To be captured into orbit, the spacecraft would be flying close to the planet and Io, taking on the heaviest dose of radiation expected during the entire mission. A great worry was knowing that energized particles might penetrate the spacecraft, causing any number of computer sequences to crash. All of the science data from the probe might be lost, or the main engine needed to go into orbit might not fire.
This was a risky thing. This is one of the riskiest things that Galileo was going to do. So I think people were, in some cases, almost terrified.
And the greatest stress, of course, as we were planning for arrival at Jupiter was the new software going to get there? Was it going to work? It was very long nights staying up, staying at work until 3 in the morning or whatever, running tests in the test bed, and just, not a lot of sleep. And everything was riding on this. I mean, it all had to work.
December 7th, 1995 was arrival day. At JPL, the press, accustomed to Voyager's encounters, was out in full force. They would be busy reporting on whether the probe survived atmospheric entry, and if so, would Galileo be successful in capturing the probe's precious data? And then, would the main engine fire to put the spacecraft into orbit? One critical event would follow another, and yet, while this would be the mission's busiest day, there was actually very little anyone could do.
On the day itself, it's all pre-canned, it's loaded in spacecraft memory. There's nothing we can do about it. If we find out that something is not going to work, it's going to be 45 minutes getting the signal from the spacecraft saying help back to the Earth, us looking at that data, scratching our heads, figuring out what's wrong, figuring out what to do to correct it, and then it would be another 45 minutes getting a signal back to the spacecraft, and an hour and a half later, it's too late to do anything. There was nothing we could do except twiddle our thumbs and sweat and chew antacids.
And unlike Voyager encounters, there would be no images to see in real time. The most the overflow crowd of guests could expect would be to know they would be the first to hear of Galileo's success or failure.
Everybody really wanted to find out as soon as possible whether the probe had worked. The mission design people actually figured out a way to get 1 bit back. We were all waiting for 1 ping.
The Galileo orbiter is a mere 1.5 Jupiter radii away from the planet and has just reached its closest approach.
Galileo was kind of an odd event in that we were used to this giant picture show with Voyager. And because of the antenna problems we had on Galileo, we knew it was going to be very, very restricted. We had all these people there to host, and we had to kind of fill in, give them something.
Okay, anything going on at the MSA yet? We can look at that again. They're still very, very patient. And hopefully later on in the day, people will be cheering, but maybe not.
We had people in a fishbowl, basically, or an aquarium. There was a glass window, and they were enclosed in this box. And in those days, we had no live audio. We'd actually call them up on the phone, and they talked to us over a phone. It was a really kind of a crazy way to do that.
We're listening and we're watching, and
there's the man.
I'm
Come
sweating.
on, Bill. Do your stuff.
We put our management in a room where they weren't supposed to be bugging us. I see the data come down. Some of us are like, yes, this looks good, but don't react. We're very much told, don't react on camera,
Right, right.
Just the same.
Big eye. Oh, there's applause.
Confirmed 693.
All right, we got it.
Telemetry lock on the probe 6.
All right, we have confirmation of telemetry lock. Everybody's... Wow, this is great.
I've never seen so much yelling and screaming over just 1 bit of data.
The probe made it. The probe survived its fiery entry into Jupiter's atmosphere. One enormous thing down today and one more to go. Hi, Bill. Give us a wave and what's happening?
We're having a great time here. I want to welcome everyone to the guest operations about to witness with us the momentous event of the first spacecraft going into orbit about Jupiter. And we are just ecstatic already because we have confirmed that indeed the probe was successful. We're just about completed with the spin-up maneuver preparatory to lighting the main engine.
It's a 49-minute burn, but I mean, if we burn for 40 minutes, would we still be happy?
There's not a lot of leeway, and if we burn for 40 minutes and stopped, we wouldn't be very happy. The consequences of it not working right were catastrophic to the mission. If we didn't get the burn off completed within just about exactly the right time, then we would have just gone flying on by Jupiter and out into solar orbit and been out there forever and no Galileo mission.
Another hour of nervous watching and waiting would have to go by before it would be known whether Galileo would become Jupiter's first orbiting spacecraft. The time was used to hear from one of the mission's most influential supporters.
Carl, welcome.
Thank you. Happy to be here.
Another encounter?
Another encounter.
Another notch in your belt.
Well, another great encounter. And I'm just so glad that after all these perils of Pauline that the entry probe entered, that the tape recorder is recording, that the burn to achieve orbital insertion is burning. All that's just terrific good news.
And he was a real mover and shaker in Washington and in the science community and in many, many communities to make Galileo happen.
We'll have actual data, hands-on data. I mean, it's really epical in the history of planetary exploration. The whole mission is.
Let's go around to the lab and see how people are reacting, waiting for the news. This is Von Karman Auditorium, and people are patiently waiting for the engine cutoff. Again, the final moment. We got something. We got an engine cutoff.
The day of arrival, all the events of the day of arrival, all rolled into one. I mean, that was the absolute ultimate. That was spectacular, that everything worked properly.
And it is my distinct pleasure to declare not only are we in orbit, but we're in a very good orbit.
Galileo certainly was the most problem-plagued interplanetary project ever. And we dealt with them all. And I guess we got our reward because on the day of arrival, everything clicked.
A lot of the questions we get are, is Galileo going to search for life? What are the prospects of life in the Jovian system? And maybe you can give us a little bit of a perspective on that.
Where might we look? The possible subsurface ocean of Europa is a very interesting environment. If there's liquid water, while we're not going to send some part of Galileo down subsurface, there's a very good chance of elucidating much better our knowledge of what's happening on Europa.
The bittersweet part of that is that Carl passed away about a year later. And that was one of the last times, it was the last time, I guess, he was at JPL.
Galileo is going to do wonders. And in just this last few months, there has been a credible announcement of a discovery of another Jupiter-like planet around a very different star, 51 Pegasi.
That's right.
And so what we're doing here is not just studying the Jupiter in our system, but in a certain sense, the whole category of Jupiters, of which, if the 51 Pegasi discovery is right, there must be an enormous number around nearby stars. So there's a whole new genre, category of things to explore. It's an epical time in the history of human exploration.
Soon after orbit insertion, Galileo began transmitting back probe data that scientists had long hoped to have.
Now, why do we want to go to Jupiter? because it tells us how the sun and planets formed from the early solar nebula, the original gas and dust cloud from which all the planets formed. Probably you all know that Jupiter is the largest planet in the solar system. The analogy I always like to make is that if you took a tomato, we sort of sampled the skin of the tomato, but we learned some very important things.
The findings were, as described in the NASA press release, startling, as they ran counter and at times contradicted some long-held assumptions.
And this arrow points to the probe entry site.
Instead of a distinct three-tiered cloud structure, there was only one. Temperatures were higher than projected, and winds were clocked at twice the anticipated speed. An expected swarm of super bolts of lightning went missing, except for a single horizontal line in an upper latitude of the planet.
There was almost no lightning occurring down anywhere else on the planet.
Nor did Jupiter's chemical composition match that of the Sun, as was assumed.
But what we found out from Galileo is that's not really the case.
The most puzzling finding, though, was the lack of H2O.
So that's been a major surprise, that the amount of water is so depleted. And that's really hard to understand. As it turned out, what happened is we probably went down into a feature that looks very much like this. This is probably a hole in the upper cloud layers of Jupiter. And what we're looking at here is what's called, quote, a hotspot. The clouds that we experienced there are not typical of Jupiter as a planet. That was sort of a minus.
The probe had descended through an area lacking in clouds. Scientists called it a meteorological anomaly, a way of saying the probe had, by chance, hit a dry hole, representing just 1% of Jupiter's atmospheric possibilities. It led one scientist to quip, "We need more probes." Meanwhile, Galileo was in the midst of its first and longest orbit of the entire mission. Up next was the first encounter with Ganymede. Ganymede is the largest moon in the solar system. If it circled the Sun instead of Jupiter, we would call it a planet. The Voyagers had shown it to be a world of rock and ice with a surface hinting of a complex and ancient tectonic history. Not much more was known.
I'm happy to report that at this time, all engineering subsystems on the spacecraft are nominal and operating as expected. To give you
It was so interesting because it was my first flight project.
Galileo is currently 27,300 kilometers from Ganymede.
The atmosphere was just intense, and I loved it, and I thought it was always like this.
So all is well, and we're looking forward to some great science data. Thank you.
We had some major surprises almost off the bat. We got images of the surface at high resolution. We found that it had distinctly different types of terrain, some of it very young geologically, with very few craters on it, but lots of ridges and cracks on it. From the beginning, one of its objectives was to look for magnetic fields in these moons. The theory says, well, probably, you know, it's not a huge rocky object, probably not hot inside, so it's probably not producing a hot molten core like the Earth to produce a dynamo effect. Ganymede had a magnetic field.
Ganymede is the only moon in the solar system known to have a magnetosphere. and measurements of it raised a tantalizing possibility: a liquid ocean under Ganymede's crust. Today, the question is not whether, but how much water lies beneath its surface. The flyby of Ganymede further reduced the length of Galileo's follow-on orbits. It was one element in a vast web of trajectories designed by JPL navigators. Time and again, they charted plots that would send Galileo skimming daringly close to the surface of a moon. The force of its gravity would be used to hurl the spacecraft towards its next intended target, all with exquisite precision. Rightly proud of their accomplishments, these mathematical wizards were known to literally dress for the part. It was another moment of levity employed to cope with the seriousness of their task. From now on, encounters would be occurring far faster, one after the other, leaving the entire team with little time to regroup. On the third orbit, the main target was Callisto. Here may be the oldest landscape in the solar system, a surface 4 billion years old and littered with scars left by tens of thousands of impacts.
Callisto, very ancient surface, and once again we got a surprise. It wasn't just ancient and cratered. The whole surface seemed to be kind of buried in dark rubble, and no evidence of a magnetic field there either.
The Callisto flyby also marked the mission's first use of a technique of lashing together an intercontinental network of giant antennas. Listening in this way, the amount of data that could be captured was increased by a factor of 10.
When your antenna has gone from a pipe to a little straw, they were constantly thinking of new ways to do things, and it rippled into every part of the operations. And that's when I first learned that when things go wrong, you also have an opportunity to fix them.
And things did continue to go wrong, often causing Galileo to go into safing, a pre-programmed response when the spacecraft senses something is amiss. The spacecraft automatically shuts down all non-essential functions and then phones home, asking ground controllers for help.
Galileo seemed to be in safing all the time. One of the big challenges there, it was a spun-despun spacecraft, so the top half spun at 3 revolutions per minute and the bottom half with the cameras was fixed. Trying to communicate from the spun section to the despun section, we had to go across a slip ring, which is kind of like a steel wool electric connection. And we found that the slip ring generated debris which caused shorts all the time.
The team could also count on safings due to radiation.
It's almost the only way you can explore these inner moons in a highly toxic radiation environment. You have to limit your exposure. Go in and come back out. Go in and come back out.
Each new orbit added to the accumulation of radiation exposure. Just how much the spacecraft could withstand before its electronics would fry and cease to work, no one knew. And where scientists most wanted to go was in close to Jupiter, to places like Io, where radiation was most dangerous. But the risk was worth it, for what Galileo witnessed at Io is almost hard to imagine. Here is a place where hundreds of volcanoes are constantly erupting. These fireworks are due to Io's location. It is caught in a tug-of-war between Jupiter, Europa, and Ganymede. This back-and-forth gravitational pull distorts Io's shape, causing extreme heating in the moon's interior. Unable to contain itself, Io erupts with massive walls of lava and plumes shooting upwards into space.
We flew by Io, and we were expecting to fly by one volcanic plume from the volcano Chvasta that we knew about from a previous orbit. And we realized that the next flyby, the spacecraft was going to go through the edges of that plume. And what we didn't know was that before that next flyby, another volcano erupted, had a gigantic plume 500 kilometers high. And Galileo went right through it. So with Io, it was difficult to plan because you might plan to avoid one volcanic plume, but you didn't know you were going to fly through another one that had never been seen before.
Jupiter is surrounded by a constellation of 79 known moons. Of them all, Europa has been the most intriguing, dating back to the time when Voyager 1 took this image from 1.5 million miles away in 1979. Here appeared to be an unusually smooth and young surface, devoid of craters. Voyager 2 traveled closer and was able to make out a patchwork of crisscrossing linear structures. Galileo's images would be even more detailed and far more revealing.
Europa was, I think, anybody's superstar of the Galileo mission. Just the first couple of encounters with Europa with Galileo just kind of blew us away.
We found a region where it looked like pieces had broken off, like an iceberg, and drifts in a watery body and twists. People who study the Arctic recognize some of these floating patterns as clearly an area where the underneath was liquid.
Some of these rafts of ice were the size of cities. There were also indications of ice flows and the possibility that water had even flowed on the surface, all pointing to the existence of a subsurface ocean.
The magnetometer came through with the final piece of data that really nailed the ocean model. It was responding exactly as if you had a big shell of salty water.
Europa, about the size of our own moon, may hold more salty water than all of Earth's oceans combined. What had once been only speculation was now deemed worthy of serious consideration. Is Europa a place where life could, or does, exist? Ironically, the question was the beginning of Galileo's demise.
So we came up with the plan to basically ram it into Jupiter and sterilize it with the energy of the impact. It's something that I still second-guess myself about, was there another way? But the problem was, the vehicle was getting old. It was having failures, and we couldn't wait too long or we lose the opportunity. So we tried to figure out the perfect time to do it. And I guess we may have been a little conservative, but not by much.
With its fuel tank nearly empty, and knowing the spacecraft could possibly have on board microscopic life from Earth, Galileo was put on a collision course with Jupiter to eliminate any chance of colliding with Europa.
Hello everyone, we'd like to welcome you to live NASA TV coverage of Galileo's grand finale. With me right now is Claudia Alexander. She is the 7th and final program manager of Galileo. We have a display right now that can actually explain what's taking place. Can you go to that right now and explain?
Yes, what we want to know, of course, is what's happening with the spacecraft. What's going on? You'll see that we've passed most of the major moons. We've passed Io, and we have passed the moons Phoebe, and we're actually going past the moon Amalthea at this moment. And believe it or not, folks, we are still collecting science data, and I am absolutely thrilled about that. We're still clicking along. And we're still doing it, so, you know, go Galileo, go.
It was very sad, trying to keep this spacecraft alive, day after day after day, doing everything we can to keep it going and keep it going. And now we know that we have deliberately told it to take a dive into Jupiter and evaporate and never be seen again. But it's also very joyful because we know we can look back at an amazing mission.
Among Galileo's firsts was delivering a probe to measure Jupiter's atmosphere. Galileo was also the first to conduct long-term observations of the Jovian system, finding evidence of subsurface water on Europa, Ganymede, and Callisto, while adding new knowledge about Io, the most volcanically active place in the solar system. Galileo was also the first to fly by an asteroid, the first to discover a moon of an asteroid, and the first to see a comet hit a planet. Galileo's legacy, though, is as much about endurance as science. It is a story of a spacecraft and its team of engineers and scientists who faced adversities and overcame them through stubborn determination and extraordinary dedication.
We all still talk about Galileo with a smile on our face, and I think of it as, you know, it's like your first love, you know, and you know, I use your first love and your first child, and there's just sense of all of these great people.
When you think about the spacecraft itself, it might be tempting to think of the pieces of metal that are its constituent parts. But for me, the ideas that it has given us will remain, and follow-up ideas, what we want to do now that we know so much from the mission, will be its legacy. So for me, the mission is much more than steel and titanium.
So the final moments, there's a small group of us sitting in the main control room at JPL here and watching the radio signal as it finally vanishes. There were a couple people who were crying. I remember Claudia Alexander, who is not with us anymore, was standing right there, and she just reached over and gave me a great big hug.
We are now less than a minute away from the end of mission. They are counting down here in space flight operations. The final moment in a great mission, Galileo is gone.
Mixed emotions. Sad to know that we won't be getting back together much as a project and seeing the people again, because these people have become our family. We care about each other. We've seen marriages and children and divorces and deaths. These people are incredibly important to you. And it's sad that you won't be sharing these experiences anymore with them and getting together and writing clever songs to poke fun at the next thing that comes along.
Good afternoon, friends and colleagues, and welcome to the first annual farewell performance of the Not Ready for Real-Time Players.
In Von Karman, we got up there, and I know I broke down in the middle of that. I think I'm starting to do that now, just remembering it.
Before one small step for man and one giant leap for mankind, a team of daring space pioneers embarked on a pair of experimental rocket projects to study the Earth and the heavens. With eyes on the sky and the future of space exploration, flight controllers inside NASA's Mercury Control Center watched America's space program take flight. And so here, the story of American space exploration began.
In the late 1950s, the earliest chapters of American space exploration were written along Florida's central Atlantic coast. Later known as the Mission Control Center, NASA's Mercury Control Center was the United States' first mission control for both unmanned and manned space programs. The Mercury Control Center controlled the flights of 3 different vehicles from 3 different seaside launch pads at the Cape. The MCC housed the program's critical launch equipment. Inside the unassuming 30,000 square foot building known to NASA as Building 1385, flight controllers monitored and controlled the Project Mercury launches and the first 3 flights of the Gemini program. The Mercury Gemini program set the stage for the highly technical challenges and accomplishments later executed by NASA Kennedy Space Center.
The Mercury program was absolutely essential to all of our space programs that followed. And the main reason being, it was the proof of the pudding that we could launch into space. We could put a man in there. We could preserve him throughout a mission. We could bring him back safely. And from there, Mercury led into Gemini, going into the Apollo program where we went to the moon.
Florida's mild climate, vast undeveloped land surrounding the Cape, and its proximity to water made it a good choice for launching rockets. And so the Mercury Control Center was designed by the Army Corps of Engineers and built in stages on Cape Canaveral Air Force Station between 1956 and 1963. The modest-looking building faced east toward the ocean, though thick vegetation hid it from view. The MCC had an inset floor and a flat roof. The exterior was designed with a pair of light metal swing doors that open onto covered entrances. Later, the famous NASA logo graced a west-facing exterior wall. Floodlights and speakers were placed along the upper roof edge. Project Mercury began in 1958, 1 week after NASA was enacted, and 3 days before the 1-year anniversary of the Soviets' launch of Sputnik.
To steal from Dickens, it was the best of times and the worst of times for the space program. Because, of course, the Russians had put up the first satellite. We had put up a satellite on January 31st of 1958, and the space race was on. Before that time, the missile race was on, and the Soviet Union was rattling their rockets at the United States, and it was a very, very tough time for our nation. So now we were in a space race at the same time, and it appeared once again we were behind.
I would have to say nothing was more exciting than working on the Mercury program because we were doing things for the first time. It was new.
The project's goals were straightforward: orbit a manned spacecraft around Earth, investigate the pilot's ability to function in space, and to recover both the pilot and the spacecraft safely. The flight control room was added to the existing building beginning in 1959 for the upcoming Mercury flights. The upgrade included a viewing area that was built by Bell Telephone Incorporated. A second addition, along the west elevation, provided additional space for support equipment. The flight control room occupied just 10% of the entire building. Christopher Kraft would be the very first flight director, and he was key in the development of the flight control operations and the first flight control team. Chris gave final launch approval. His console was equipped with a black and white monitor, and he had access to every communication circuit, called loops.
But in the final analysis, it had to be this gentleman right here, Chris Kraft, as flight director, running the entire show, and that's what made it work. Chris was an amazing person. He's the only I'm a communicator, and he's the only person I ever saw that could listen and understand 8 intercom nets simultaneously. I know people always tease him about that, but that's just he's the only person I know that could do that.
So the combination of the two, between guys on the ground and a crew in space, really was a phenomenal thing in its time. I think we were able to get a lot done, more done than had we not had a control center.
We had the Mercury Control Center right there, right adjacent to the press site, actually, and Chris Kraft was the flight director. Walt Williams was the operations director, and you had a number of other key people who grew up in that program and carried us all the way to the moon as far as flight control was concerned. They had a fantastic worldwide map in there because they wanted to cover the orbital flights that would follow on the Mercury Atlas.
The MCC was part of the Spaceflight Tracking and Data Network. The tracking network provided communication between the capsule and mission control with an impressive system of ships on 3 oceans and 18 ground stations on 3 continents. As part of this worldwide network of tracking stations, a 2-dimensional world map and 2 large projector boards dominated the front wall of the flight control room. The map used a series of circles to pinpoint tracking stations. To keep continuous track of the Mercury spacecraft, a mini-spacecraft model suspended by wires traced its orbit. The projector boards were used to display flight measurements plotted by sliding beads. Trend charts displayed the astronauts' condition. Goddard Space Flight Center in Greenbelt, Maryland was the link between the remote tracking stations and the MCC. As Project Mercury took shape, so too did the first astronaut corps. Leroy Gordon Cooper, Virgil Gus Grissom, Alan Shepard, Walter Wally Schirra, Donald Deke Slayton, Scott Carpenter, and John Glenn became known as the Mercury 7. They were in training as teams prepared for the upcoming flights. Inaugural operations inside the MCC supported the first Mercury Redstone launch attempt. The MR-1 launch on November 21, 1960 from Launch Pad 6 was classified unsuccessful, but proved many of the systems designed for the vehicle and capsule worked. MR-1A successfully launched a few weeks later on December 19, 1960. The same spacecraft was used. About 6 months later, astronaut Alan Shepard made history with his suborbital ballistic flight on May 5, 1961.
So this was a very significant flight because the country needed this. The whole free world needed this flight at this time.
A Mercury Redstone rocket, MR-3, known as Freedom 7, lifted off from Launch Complex 5-6 at 9:34 a.m. Eastern Time. It was the first manned flight controlled by teams inside the MCC, and it lasted 15 minutes.
It was a beautiful, beautiful May morning. And I was in charge also of the telephone, the intercom service for the control center. And I was also in charge of the air-to-ground. So I had a fairly busy time during all of the launches. But obviously there was an air of excitement in the control center on that first manned flight that you couldn't duplicate anywhere in the world.
That very first flight on that Mercury Redstone, I mean, going up into space and coming back down, even though you didn't orbit the Earth, that set the stage for everything else that we've done.
As the command center, the MCC had 8 primary functions: to direct all aspects of the capsule's flight, monitor the health of the astronaut and the system status of the capsule, make decisions to abort a mission, determine the proper procedures following an abort procedure, command the re-entry of the capsule, keep the astronauts and all the tracking stations informed of the mission's progress, coordinate and maintain the flow of communication between all tracking stations, and inform the recovery forces when the capsule would re-enter the atmosphere. It would take 14 flight controllers to meet these mission objectives. The first critical row of flight control seats was coined the trench. One of those important positions was the capsule communicator, or CAPCOM position, one held only by an astronaut.
I think the CAPCOM today is very much the same as it was back during the early Mercury days. It's that point of contact with the crew. It provides the crew perspective to the control team. Yeah, very similar.
Public interest in the space program and the astronauts grew as Project Mercury realized much success.
Because the beaches were loaded. The program was pretty small. It was only about 350, 400 people, and it was real excitement. The cities around here were growing. The center was really on its way.
News of the Mercury missions was in the newspapers and on TV.
I've had the pleasure of covering every launch of American astronauts from Cape Canaveral, Florida.
Shorty Powers was the first public information officer for NASA. He was the voice of mission control.
We had a red light that would come on our desk. And that red light was a signal that Mercury Control would have a report in 30 seconds.
Some employees at the Cape were just as excited about the astronauts and the missions as the public.
I met all the original 7 astronauts because they would come into the ready room. Well, they were excited like everyone else, and everything was new to them. And they would all come through because each one was interested, of course. It wouldn't just one come through, they all would come through.
The Mercury Atlas and Mercury Redstone vehicles flew 26 missions as part of Project Mercury. 6 of those were manned flights. The first orbital flight for the Mercury program was MA6.
Roger, backup clock is started.
Astronaut John Glenn performed it on February 20th, 1962. Astronaut Scott Carpenter followed Glenn's successful mission with his own orbit of the Earth later that year.
Climbing into that spacecraft and sitting on the top of the rocket was something we had simulated time and time and time again. So, in a certain sense, it was just another day at the office, except this time you realized that it was for real.
MA9 was the last flight of Project Mercury, piloted by Gordon Cooper on May 15, 1963, in his spacecraft named Faith 7. He was the last American to orbit the Earth solo. The mission lasted 1 day, 10 hours, 19 minutes, and 49 seconds.
I named my spacecraft Faith 7 for 3 reasons. 1, because of a belief in God and country. 2, because of a loyalty to organizations, to the 2 organizations actually, which I belong. And 3, because of a confidence in the entire space team.
The Mercury program was ending, and America's second human spaceflight program was soon to begin in support of one very clear mission.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Bridging the gap between Mercury and Apollo was the Gemini program. Following the Mercury program, Gemini subjected astronauts to long-duration flights in support of the upcoming Apollo moon missions. Gemini accomplished 10 manned missions and 2 unmanned, each on a Titan II launch vehicle from Launch Complex 19. 2 astronauts flew in the capsule, which is how it got its moniker, Gemini, or Twin. Renovations to the MCC were completed in 1962 and in 1963 in support of the Gemini missions. An addition wrapped around the east, north, and most of the west and south sides of the MCC. New areas included space for flight control briefings, data analysis, and room for a new Gemini spacecraft trainer. The old trend charts on either side of the world map were replaced by rear projection screens. The world map displayed new tracking stations, and one clock above the map changed to estimated liftoff time. A desk for a public affairs officer was also added, along with a pair of consoles on the left side of the room facing inward for the support control coordinator and the display coordinator. After the conclusion of Gus Grissom and John Young's flight of Gemini 3 in March 1965, NASA transferred mission control to Houston, Texas, where it still resides today. After mission control functions were relocated to Houston, Texas, the Mercury Control Center provided backup for the initial launch and the trajectory for the remaining Gemini missions. In 1967, the MCC became a tour stop for guests visiting NASA's Kennedy Space Center Visitor Complex. A bus tour provided the public an opportunity to look through the glass windows of the viewing room and see where the first chapters of American space history were written. It was a popular attraction from 1967 through 1995. In the late 90s, the building began to show signs of aging. In an effort to preserve what remained inside the deteriorating structure, NASA removed the artifacts inside. Later, a plan was developed to create an authentic MCC flight control room exhibit at the KSC Visitor Complex.
The opportunity for relocating this amazing room full of history was to offer it to many, many more people. Accessibility to the actual facility was becoming more and more challenging, and it allowed for the consoles throughout the room to be displayed and preserved. Had they been left in the building all those years, they would be in terrible condition right now.
The exhibit is inside an 8,500 square foot building dedicated to early space exploration.
One piece at a time, we carefully removed it, brought it over. So what you see here is a duplication of the actual MCC, the Mission Control Center, with the screens, the consoles, the flooring, the finishes, and of course the tracking board. The consoles themselves, though, are completely authentic. The tracking map is completely authentic.
Guests get a memorable and authentic experience.
I think it's an amazing opportunity for our guests to look through the glass and step back in time and honor the heroic first years of our space program.
The MCC was designated by the National Park Service as a contributing structure to a National Historic Landmark District in 1984. The district consists of 7 other contributing properties: launch complexes 5, 6, 13, 14, 19, 26, and 34. NASA determined the Mercury Control Center was no longer needed for NASA missions and had deteriorated beyond repair. Final artifact preservation efforts began in 2009. The Mercury Control Center controlled the flights of 3 vehicles from 3 launch pads during its years of service. In March 2010, heavy equipment operated by NASA contractors leveled the concrete block and metal building.
It's a transition, but we have to be energy efficient. We have to prepare for the future. We've got to prepare for going beyond low Earth orbit and doing bigger and better things. And this is all part of the process as we grow and change here at the Kennedy Space Center. We will never forget our heritage. It's crucial to us. History is important.
My name is Sophia Von Hippel, and I'm an intern with GSFC, and I'm working on a deep learning project looking at climate data.
Hi, I'm Myra Ostajani, and I'm currently a software engineer intern at GIS. I'm working on a project which is advancing the snow ice cloud mask over Greenland.
Hi, my name's Alina. I'm working on RSP monitoring and data management at GIS with Goddard Space Flight Center in Maryland.
Okay, my name is IODs, and I'm a graduate student intern with NASA GIS.
I've been working on creating a training data set and also the training code for a deep learning model.
Yeah, so specifically I've been developing a lot in Python. I've been creating a lot of data analysis scripts, and I've been using different tools such as Tableau to visualize certain data, right?
Currently, I'm working on an app that displays all the data collected by the RSP instrument.
I'm working with a team that looks at how to characterize remote sensing and land surface temperatures within Brooklyn, New York.
I think for me, over at Wallops, it's been a pretty good session. So a lot of stuff that I did, like where I was at Greenbelt, was like social media stuff, but at Wallops, they do a lot of internal video projects.
I was really excited to get to help out with live shots for the Sentinel-6 launch, which was not something I expected to be able to help with during this internship.
You're on mute.
Still on mute.
You're still on mute.
Logging into Microsoft Teams, the snap filter was not turned off. So instead of my face actually showing up on the screen, I had a pink wig that I was using to entertain my students, but I entertained my NASA team as well.
Thanks for the test. That was good. Hello. Too late. We saw you.
Sorry.
Today, actually, I forgot to unmute myself, and I think they heard like TikTok or something in the background.
I have a feeling it's his headphones. Let's see.
Other NASA centers, I'd just be...
I think your VPN might have gone out.
Carl's on mute. Get paid.
Hey, what's up, everyone?
There we go.
There he is.
Yeah.
Been a good meeting, and it's been our last one for the fall, and I'm going to miss you all. But I'll see you on Wednesday for the presentations, and that's all I've got for today. So have a good rest of your Monday.
Thanks, Carl. Bye,
Thanks,
everyone.
Carl.
Bye.
Bye.
Hi, I'm Dr. E. Ellen Stofan, and Dr. Z, Dr. Thomas Zerbuchen, and I would like to answer some of your questions. We got a question, which I think you and I only have one answer to. It says, what should I study in the field of space science, and why should you study it? And you and I have different reasons, so I'm curious to hear yours.
So first of all, should you study space science? Absolutely. It's a great subject area, and there's many different ways you can get into it. I actually believe the two of us have a different degree. I is a PhD in astrophysics. There's others that I know that went through engineering and so forth. And for me, what's really interesting is as we build teams, these resilient teams that make these missions happen, it takes many of us with different backgrounds coming in and study whatever it is that you're most excited about. For me, that was astrophysics, and I'm really glad I did that. I focused on the sun, but you studied something else, right?
Yeah, I studied planetary geology, and this question was one of the reasons I wore my Cassini-Huygens shirt today. I worked on the Cassini mission looking at one of Saturn's moons called Titan, and we had people who were geologists, people who studied the atmospheres. We had people who studied the rings of Saturn. We had people looking at the solar wind out in the vicinity. So you had all these people from all these different disciplines, and we were all space scientists and all working together to really try to understand Saturn and its crazy system of moons. So to me, it's the best field because it's fun. There's so much to figure out. And with data coming in from new telescopes like James Webb, we're never going to be short of puzzles for people to be working on.
So I want to ask one more question. I'm really curious about the answer, and it's really about you personally. What obstacles did you encounter as a woman in your career as a scientist, as an administrator first at NASA, now at the Smithsonian, and especially as a little girl curious about science? How did you overcome it, and who helped you along the way?
Well, I look back to my own personal experience and say, well, how did I as a young girl get involved when so few girls did? One of the things I really think about the fact is I had parents who hugely supported me. I had teachers who hugely supported me. And it wasn't till later in my career where I encountered obstacles and a lot of men who clearly thought I really didn't belong in the room. I got called little girl after I'd had a child by someone who actually worked for me. I did eventually encounter that kind of treatment, but by the time I did, I was a lot further on in my career. So I really think about how can we better support kids who may not have that support network of teachers and parents. How do we, as the science community, really reach out to kids and say, you know, science is a great field? The other thing I really think about, and it's something I work on a lot at the Air and Space Museum, is when I was a kid, I looked for women role models. I looked for, were there women out there in science doing cool things? And I would find biographies of Marie Curie, and that was about it. And I loved reading stories about Mary Leakey discovering the origins of life off in Africa. So I really looked for those women role models, and they were so hard to find. So as we reimagine the National Air and Space Museum, as we're redoing all the galleries, I really think about whose stories are we telling? And are we telling stories so that every kid, no matter what they look like, when they come in the museum, they understand that people who look just like them have been here all along doing amazing things in science, in technology, because we have to broaden out our fields. We have to make everyone feel welcome, or else we're not tapping into the talent of all of our population.
Well, I really want to thank you for being a role model yourself. I remember introducing you to my daughter, and kind of the director of the Smithsonian, and of course, as distinguished scientist. What a role model you have been, and thanks for that. You persevered and pushed through. There's challenges ahead of us, and I really want to thank you for being just a role model for so many.
Thanks so much. This has been really fun, and I can't wait to do our next episode of Easy Science.
3, 2, 1. Ignition. And liftoff.
Copy, 1 Alpha. Vehicle pushing downrange. Trajectory nominal.
Attention! NASA television programming on Galaxy 13 is moving from transponder 11 to transponder 15. The transmission modulation format is now DVB-S2 8PSK. This move is in line with the Federal Communications Commission's initiative to free up C-band bandwidth on domestic satellites in support of future 5G terrestrial communications efforts. Transponder 11 and 15 are both active during this transition. Distribution of NASA TV programming on Transponder 11 will end on August 29, 2022. For more information, go to nasa.gov/NASA-TV.
Did you know that if you were born after 2000, during your entire life there has been someone living in space? That's thanks to the International Space Station, which celebrated its 20th anniversary of continuous human habitation in 2020. You've probably heard a lot about the incredible science that happens on board the station, but the outside is actually prime real estate for all kinds of experiments and technology development too.
The International Space Station is a great platform that demonstrates service and technology because it provides power, data, there's robotics in space.
With Tech on Deck, we'll be talking about some key experiments that have taken place outside in the harsh environment of space, which will help us advance human exploration.
Nexus is NASA's Exploration and In-Space Services Project Division at the Goddard Space Flight Center. The goal of the division is to usher in a new era of more sustainable, affordable, and resilient spaceflight, both near the Earth, around the Moon, and deep into the solar system. Many members of the Nexus team started off with the Hubble telescope servicing missions. We've taken that technology, applied that to robotic servicing.
From robotic refueling missions that will help spacecraft live longer and journey farther to autonomous navigation systems, NASA's Exploration and In-Space Services Division has taken advantage of the wonderful opportunity station offers to test new technologies. As we look to exploring our solar system and beyond, and establishing a sustained human presence in space beyond low Earth orbit, many of these technologies will play a key role.
We use the robots on space station to demonstrate the technologies needed to enable satellite servicing in the future. We've also used the robots on space station to do some of the more repetitive tasks or the dangerous tasks that astronauts shouldn't be doing, like going outside the space station to try to look for ammonia leaks. Robots are very good at moving fine, delicate positions, moving back and forth, doing those sorts of tasks that would be challenging for humans to do.
In order to live in space, astronauts will first need to reach their far-out destinations like Mars. This will require refueling and replenishment of oxygen supplies, things the robotic refueling missions worked to demonstrate on station. They will also need to be able to construct, maintain, and repair their habitats, as well as adapt to unforeseen circumstances.
Because we're in space in low Earth orbit, we have lighting conditions that are representative of objects in space, and so allows us to launch tools and modules into orbit, put them on the space station, and then use those robotic technologies and all the infrastructure that comes with the space station to mature those technologies in a way that's much, much less expensive than if we try to launch our own satellite and demonstrate those for the first time, not using the space station.
For these endeavors, Nexus's work with astronaut tools, satellite servicing, and on-orbit assembly and manufacturing will do the trick.
We develop the technologies that are needed to advance exploration in ways you can service satellites in the future, build satellites and build structures on orbit, refuel satellites on the way to other planets, repair those satellites much like we do on that side of space station. Both humans and robots are used to maintain habitats in space. We're developing technologies that can be used by NASA and others to make those a reality.
The International Space Station is the perfect testing ground for technologies that will be used to propel humans farther than we've ever gone before. The station is helping us build the necessary foundation to make it possible. Outside of the International Space Station, space can be a lonely place. Most satellites are designed to live their lives alone, and we've yet to find life outside of Earth. This means that when we launch a spacecraft or satellite, for the most part it's on its own, and has a limited lifespan based on when critical items like fuel run out, or something breaks. You wouldn't throw away your car if it ran out of gas, and thanks to the advent of modern-day robotics, software, and computing power, we will soon be able to apply that logic to satellites. We are on the cusp of breaking the one-and-done paradigm that exists for most satellites. An important step in that direction is NASA's Robotic Refueling Mission, or RRM, demonstration on the International Space Station. Because refueling a satellite that was not designed to be refueled has never been done before, practice is key. With that in mind, the first two phases of RRM took place on station from 2011 to 2017 and tested the tools, technologies, and techniques to refuel and repair satellites in orbit.
RM and RM Phase 2 were designed to demonstrate end-to-end refueling of a spacecraft, as well as the first steps of cryogenic refueling or replenishment. We wanted to use the robot on the International Space Station to be able to demonstrate the technologies and techniques to do this refueling, so we built innovative tools to bridge the gap between the robot and the payload interfaces.
Consisting of a module or box affixed to the outside of station and robotic tools, the demonstrations use station's Dexter robot to operate tools and test servicing tasks such as cutting and peeling back protective thermal blankets, unscrewing caps, turning valves, transferring fluid, inspection, and intermediary steps leading up to refueling.
Once we were all done, we were able to transfer fuel end to end through a spacecraft fill and drain valve that wasn't designed to be robotically refueled.
The RRM demonstration helped test and prove technologies that will make refueling satellites not designed to be refueled possible, something that will be further demonstrated by NASA's On-Orbit Servicing, Assembly, and Manufacturing 1 mission. But it also helped to lay the groundwork for designing future satellites in a way to make them more easily serviceable.
These missions were important because we needed to demonstrate in orbit that this technology was ready. There were a lot of people that felt that at the time of RRM that the technology was so far in the future that they didn't feel what we were talking about was possible. So we needed to demonstrate in orbit this technology so that we could start changing the paradigm and incorporate these technologies into the future spacecraft designs and missions.
RRM Phase 1 and 2 were all about preparing an interface for refueling, which in many ways is half the battle. To robotically refuel a satellite, you need to perform a series of highly dexterous tasks to even access the valve. The next step is to actually perform refueling tasks, which is what the next phase, RRM-3, has been demonstrating on station over a series of operations since 2018. RRM is a critical piece of the sustainable spaceflight puzzle that helps us with the ability to robotically refuel, repair, and maintain satellites in both near and distant orbits, well beyond the reach of where humans can go today. For generations, Mars has beckoned. Now, the red planet is within our reach. But how do we get there? The key is in the details, and in the technology. First and foremost, you need fuel. This is not only true for getting to Mars, but for any form of deep space exploration. Being able to replenish fuel on a long-duration journey means massive amounts aren't needed up front, freeing up space for other important things. Enter Robotic Refueling Mission 3, or RRM-3 for short. This demonstration launched to the International Space Station in December of 2018 and has helped us develop tools and techniques needed to replenish cryogenic fluid in space. Transferring cryogenic fluids has never been done before in space. These super cold fluids can be used as propellants, coolants, or for life support systems. Being able to replenish these fluids that run out, otherwise known as consumables, is an important part of the sustainable exploration roadmap. Not just for Mars, but for NASA's Artemis program, which will land the first woman and the next man on the moon. Since refueling cryogenic fluids in space has never been done before, RRM-3 tested the technologies and techniques needed to make that possible. First, we sent the RRM-3 payload and its 3 main tools to space station, where astronauts assembled the parts.
When I was living aboard the International Space Station in the spring of 2019, I was fortunate enough to take part in the very small part in the Robotic Refueling Mission 3. And my job was to unload the components of the actual RRM-3 from one of our visiting vehicles, and we take it into our Japanese experimental module, the GEM, where we have an airlock. And right inside of the airlock, we unpacked all of the boxes, much like you would a piece of furniture that you had to assemble yourself at home. So unpacked all of the pieces, we did a checkout. We worked with the ground, we got everything assembled, and then we placed it into the Japanese airlock. And from there, we were able to put it outside of the International Space Station. So my involvement in RRM-3 was the physical final assembly of the actual components.
RRM-3 was delivered to the space station by a SpaceX Dragon on the company's 16th Commercial Resupply Services mission and installed on the outside of station by the Canadian robot Dexter. Dexter then picked up the tools from the JEM airlock and installed them onto the RRM-3 payload. The ground operations team was now ready to begin operating the 3 tools to test how they would work in space. For the first set of operations, conducted in August 2019, Dexter used one of the RRM-3 tools to prepare the RRM-3 module's interface for transferring cryogenic fuel. The second set of operations was then conducted in October 2020. For these, Dexter used one of the remaining 2 tools to insert an 11-foot-long hose in an open port and the other snake-like camera inspection tools simultaneously to verify the hose's position in the inside of RM3's tubing. This marked the first time that Dexter had tools in both arms working the same tasks simultaneously. The RM3 demonstration added experience and information to NASA's knowledge base on the storage and transferring cryogenic fluids in space. It is currently still on station, where it will conduct one final set of operations in mid-2022. For getting to the Moon, Mars, and beyond, cryogenic fluids will be used as propellants and to maintain life support systems for astronauts. The Mars atmosphere is made up of carbon dioxide, which could be converted to liquid oxygen, a type of cryogenic fluid that could be used both as propellant and for breathing. Astronauts may be able to fuel rockets or replenish their oxygen supplies using compounds found in the Martian atmosphere. A tool on the Mars Perseverance rover called Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, is set to demonstrate the first ever conversion of Martian carbon dioxide to oxygen, which is another important piece of the puzzle. In order to make a sustained human presence in space a reality, humans and robots will have to work together using technologies like those developed by RM3 and MOXIE.
A lot of people ask about, whose job is exploring outer space? Is it robots or is it humans? And I believe that it requires teamwork between robots and humans, and that our exploration is not complete or even possible without both. So robots can go farther, they're less expensive, and they can go for longer periods of time. They don't require as much maintenance. You don't have to feed and care for a robot, much like you do if you send me back to space. So like the Mars rovers, the Galileo that explored Jupiter and its moons, the Hubble and the soon-to-be James Webb Space Telescope, they are doing missions in locations that humans, to this point, don't have the capability to go. There's also something very important about humans wanting to know what it's like to be there. It's not enough for humans to take a picture of Mount Everest or Antarctica and say, oh, okay, that's what it looks like. The human condition is we are born to explore. We're born to say, what if? What's just beyond what we know? And what is it like to be there? And so the human side of space exploration, first of all, it's orders of magnitude closer to Earth. We have not been able to send humans nearly as far as we've been able to send robotic probes. But they're 2 very different missions, and they serve a different type of curiosity.
Mars and deep space are calling human explorers, and RM3 is a step toward helping NASA answer that call. Though it sounds complex, the idea is simple. Having the ability to refuel will allow NASA to embark on longer journeys to explore the depths of our solar system. Did you know there's a 3-eyed raven currently perched on the International Space Station? Not an actual bird, but rather a technology payload that is helping NASA develop a relative navigation system, or autopilot, for spacecraft. Launched to station in 2017 aboard a SpaceX Dragon on the company's 10th commercial resupply services mission for NASA, and installed on the outside of ISS by station's Dexter robot, Raven is equipped with 3 distinct camera vision systems: visible, infrared, and LiDAR. Combined with NASA-developed software algorithms, this rotating module of technology keeps a weather eye on arriving spacecraft. Raven's head, containing its 3 eyes, or cameras, is always on the swivel, which is made possible by its integral gimbal.
Raven is an on-orbit test bed that was built to mature technologies related to relative navigation sensors and algorithms. Raven was launched to the International Space Station aboard a SpaceX Dragon capsule in February 2017, and it's been operational on the space station since that time. So using 3 different sensors on Raven that are on a movable gimbal platform, Raven can track the incoming visiting vehicle to station all the way from very, very far away, all the way up to where they dock with the space station. So basically, at any given time, Raven can tell you where the incoming visiting vehicle is in space relative to the space station and what attitude or pointing direction it is.
Raven sends the data it collects from tracking and observing incoming spacecraft to its processor or brain, called Space Cube. This information then tells Raven how it needs to move to continue to track the spacecraft and gauge relative distance and positioning. NASA engineers have taken what they've learned from multiple Raven observations over the years to adjust and fine-tune the relative navigation system as needed, so it's ready for the upcoming on-orbit servicing, assembly, and manufacturing 1 mission, which will robotically refuel a satellite, among other things.
Raven is a sensor system that can image an object, process those images on board in real time with advanced algorithms, and calculate the pose of the object relative to itself.
These factors come together to create something like spacecraft autopilot. Much like a self-driving car can maintain cruise control based on the speed of the vehicle it follows, 2 free-flying spacecraft will be able to dock with one another using this technology. Though this operation is similar to the autonomous docking of visiting spacecraft to station, Raven's unique application is necessary for docking 2 satellites with the challenges of each moving and rotating in every direction during the rendezvous and docking phase.
Using that information to then guide the first spacecraft to autonomously rendezvous with and dock with the second spacecraft. So that means finding it in space, aligning with it appropriately, and then bringing the 2 vehicles together without smashing them into and destroying each of them, all without human intervention.
This capability is the kind of thing you need for docking with spacecraft that were not originally designed to be docked with and serviced, which happens to be a vast majority of them. That's why Raven's time on station is critical for the future of on-orbit servicing, assembly, and manufacturing, or OSAM. The OSAM-1 mission will use Raven's relative navigation capability to autonomously, meaning no humans involved, rendezvous and dock with the satellite, and then telerobotically refuel it. This will be the first time in history a spacecraft not originally designed to be serviced will be refueled as a means to extend its operational life. Raven is also important for future exploration missions.
Raven's technologies can be applied to future NASA missions because if humans want to make a footprint in the solar system beyond low Earth orbit, which is where the International Space Station is located, we're going to have to rely on some form of autonomous docking technologies in the future. Whether it be an unmanned cargo vehicle meeting up in orbit around the moon, refueling tankers located in geosynchronous Earth orbit, or a return vehicle arriving on Mars in advance of a crewed landing, all of these feats will require the technology we're developing with Raven.
Using its 3 eyes, Raven is looking to the moon, Mars, and beyond.
Relying on highly robust autonomous systems becomes more crucial the further you move away from Earth as the communications time increases drastically. Once you move past low Earth orbit, it becomes very impossible for humans on Earth to do these highly complex maneuvers in real time. It's more efficient to allow computers to perform these sequences autonomously without human intervention.
Although Raven has successfully concluded its main mission objectives, it remains on station. Meanwhile, its team on the ground is using what they've learned to develop more never-before-seen technologies that will enable future space exploration.
Before I started digging in that other bag, here you go. No problem.
If you need to fix something in space that wasn't designed to be fixed, it's going to take all the experience you can get. With that in mind, when the International Space Station's Alpha Magnetic Spectrometer, or AMS, needed repairs, NASA's Johnson Space Center and Goddard Space Flight Center used their joint expertise to make it happen. At Goddard, that expertise resides in NASA's Exploration and In-Space Services Division, or NEXUS, which evolved from the office that was responsible for the Hubble Space Telescope servicing missions. Key to these missions was the development of specialized tools. While you've probably heard of Hubble, you may not be as familiar with AMS, so let's start there. Designed for a 3-year mission of sifting through cosmic ray particles, AMS has been looking for signs of dark matter from its position on station since 2011. Hundreds of researchers have used the data collected to investigate the source of the mysterious substance to help us better understand the origins of the universe. To continue this important data collection, AMS needed an upgrade due to general wear and tear from the harsh environment of space, specifically a new cooling system. A repair could extend its life beyond what was originally planned. Sounds easy enough, right? In fact, due to the instrument's complexity and the fact that it was not designed to be repaired, even gaining access to the system to replace it was difficult. AMS's design did not incorporate the kinds of interfaces that make spacewalks easier, or have the ability to be serviced with traditional multi-purpose tools. And so, over the course of 4 years, NASA got to work designing and developing some of the most complex spacewalks since the Hubble servicing missions in the 90s and early 2000s to fix AMS.
The AMS tools themselves were unique. They were built specifically for this task, a task that was never intended to be performed on a spacewalk. And so that required a lot of thinking about how we were going to get inside so that we could access the tubes that we needed to cut into and then install the new thermal control system, but also how to put handling aids on it so that we had a place to attach our tethers, to attach our foot restraints, to have handholds, have a place to attach equipment that we needed out there.
NASA developed 20 specialized tools to make the job possible, and on November 15, 2019, astronauts Andrew Morgan and Luca Parmitano got to work. On this first spacewalk, astronauts needed to get access. By design, 5 of the tools could be seen floating off into space, attached to the debris shield that was removed to give the astronauts access to the heart of AMS.
The debris shield handling aid was one of the first tools that Luca installed on the EVA, and this gave us a handhold to install on the debris shield to work from, but also a handle for me to hold on to ultimately when we jettisoned it overboard to the aft side of the ISS, which was a lot of fun to do.
The astronauts continued with 3 more spacewalks over the next 2 months, using all of the specially designed tools. One such tool was the Tube Cutting Guide, which was a direct result of multiple practice sessions at Johnson Space Center facilities like the Neutral Buoyancy Lab. While practicing, astronauts communicated the need for a way to identify and verify the correct tubes to cut, since they all look the same to the astronauts' eyes within the spacesuit.
After we had removed the debris shield and the VSB cover, now we have the tubes exposed, and we actually had to cut into those tubes in order to pull out the correct ones to connect with the new thermal control system, the new pump. In order to do that, we had to be very sure of the tubes that we were cutting. These ingenious tube cutting guides installed over the top of the tubes and made sure that we knew and we were communicating correctly with the ground team to make sure that we were cutting the correct tube at the right time.
In January 2020, Luca Parmitano and Drew Morgan completed the 4th and final spacewalk to repair AMS. Because of their work and the ingenuity of tool designers and engineers, the instrument is now back in commission and able to continue to collect data about the origins of our universe for years to come.
People from Goddard and JC spend a lot of time developing these tools with their knowledge and the support of astronauts like Chris Cassidy. And we are very thankful that we were privileged to use those tools and to put them to very successful use. Thank you very much.
The move to the launch pad ahead of our Artemis 1 flight test, discussing priorities for national space activities, and cargo and science head home from the space station. A few of the stories to tell you about this week at NASA. On the night of August 16th, teams at our Kennedy Space Center began the approximately 4-mile move of the Space Launch System or SLS rocket and Orion spacecraft from the Vehicle Assembly Building to Launch Pad 39B in preparation for the launch of our uncrewed Artemis 1 flight test. The rocket and spacecraft arrived at the pad the next morning. Artemis 1 is the first in a series of increasingly complex missions to help us establish a long-term presence on the Moon. The mission also will serve as a stepping stone to sending astronauts to Mars. Artemis 1 is currently targeted for launch no earlier than August 29th. Vice President Kamala Harris recently met with the National Space Council at the Chabot Space and Science Center in Oakland, California, the official visitor center for our Ames Research Center. Aerospace companies at the event had the opportunity to display and share their work with the Vice President. The Vice President, who serves as the chair of the National Space Council, also made a speech in which she discussed upcoming priorities for national activities in space, including strengthening public-private partnerships and the benefits of space exploration for all. On August 19th, a SpaceX Dragon cargo resupply spacecraft left the International Space Station and headed back to Earth with more than 4,000 pounds of supplies and scientific experiments for NASA and others. This was SpaceX's 25th commercial resupply services mission for NASA. Another asteroid has been added to the to-visit list for our Lucy spacecraft. Lucy's science team recently discovered that the smallest of the mission's Trojan asteroid targets, Ptolemy, has a moon. With this discovery, Lucy is now on track to visit a total of 9 asteroids, 1 main belt asteroid, and 8 so-called Trojan asteroids, a previously unexplored population of asteroids that lead and follow Jupiter in its orbit around the Sun. Our Wallops Flight Facility in Virginia recently helped teams of U.S. college students launch their technology experiments into space. The experiments were launched on a Terrier-improved Malamute sounding rocket to an altitude of about 91 miles before descending back to Earth by parachute. The investigations were flown through the RockSat X program, which gives students the experience of building experiments for spaceflight. A quick note about an upcoming change for NASA television. NASA TV programming on Galaxy 13 domestic satellite is moving from transponder 11 to transponder 15. Currently, both transponders are active, but distribution of NASA TV programming on transponder 11 will end on Monday, August 29th. For complete details, please visit go.nasa.gov/transponder. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
Hi, interview is yours.
Thank you. Good morning. Good morning, Frank. Can you hear me?
Hey, Gina, good morning. Yes, I can hear you. How do you hear me?
All right. So here you are, getting close to launch, but I want to take you back to your astronaut application process. So how complicated was it? What do you think tipped it for you? And what was that phone call like when you were selected?
Yeah, it was an exciting process. Gosh, it was almost 2 years long. And really, you don't start getting excited about it, I think, until the very end. At least I didn't. I don't know, who knows what tipped it for me, right? I count myself incredibly blessed and very lucky. One of the really neat things about the process is you get to meet all these amazing other people that are applying. And you quickly realize, like, any one of them would make an awesome astronaut, even though you don't have a really good idea of what an astronaut exactly is at the time. They're just amazing people. And so, honestly, when I was picked, I was completely surprised. I got a little emotional because I completely did not expect it. But yeah, what a blessing. And I'm glad to be here. And I can't imagine that, 5 years later, I'm getting ready to launch. So it's pretty exciting stuff.
Well, you've flown helicopters, you've jumped out of airplanes, you're a flight surgeon. I mean, really, what are you most looking forward to this launch?
Yeah, I think just the whole experience, right? There's a lot of things about it that I've been excited about for a while. The launch itself, right, has got to be pretty amazing to get on a rocket and finally launch. And then quickly after that, you become weightless, and then you're going to be weightless for 6 months. And I think that's going to be a pretty neat experience. And I think the learning curve in space is incredibly steep. And so just the fact that I'll be in an environment where I'm constantly learning, constantly getting better at something new, I think that'll be pretty exciting. And then when you go to undock and come back home and you re-enter the atmosphere, I mean, that's a pretty exciting moment too. So I think the whole 6-month experience is going to be pretty awesome.
Well, one of the skills that you're bringing to the space station is going to be, I think, incredibly useful as we go further into space to Moon and to Mars. You're a flight surgeon. You are a doctor and a flight surgeon. You bring these skill sets to this mission. So how will you use this during your time on the space station? You'll sort of be observing yourself, I think.
Yeah, that's one of those skill sets you hope to never use, right? But I think the biggest thing that I bring besides the knowledge and the skill set is really more adaptability, right? Just having spent 24 years in the Army and in medicine in general, you just learn to adapt because you never know what's coming around the corner. And just being able to handle those things and kind of stay cool under pressure, or at least pretend to be, right? Even if you are nervous about it. I think all those things will really pay off more than anything else.
Well, there's so many things we need to learn about the human body before we go to live on the moon and hopefully to Mars. Radiation exposure, your bones, all of that. So let's talk a little bit about the research that hopefully you'll be getting to do on the space station that will help us learn how to live on other planets.
Yeah, that's one of the really neat things about this, right? We've been doing this for about 20 years, and it still feels like we learn something new every day, especially about human anatomy and human biology. Things that were a huge concern initially, right? Bone density loss. We've kind of figured out how to get around that a little bit through exercise and resistive training. And so as we keep moving forward, I think we're going to get better and better at the other tough hurdles, radiation being one of them, how your changes in blood distribution affect your heart and your vascular system. And then just the prolonged, even though we're staying on station now for 6 months to a year, eventually when we get to Mars, we're thinking that's going to take 3 years or so. So that's a huge difference. And so just knowing that every day we're contributing to that knowledge base that will hopefully help humans achieve something that we could never dream of now. I think that's just a really gratifying thing.
Well, I know you won't be at the Kennedy Space Center for the Artemis launch next week, but I'm assuming you'll be watching it wherever you are. And then Orion will be orbiting the moon when you're on the space station. So how closely will you be monitoring that mission when you're up in space?
Yeah, well, first of all, I'll tell you, the launch, I sure do wish I could be there, right? Regardless of being an astronaut or not, I think everybody will probably feel just like a little kid again watching that rocket launch. It's just going to be amazing. I hope to watch it live. Unfortunately, our training is pretty heavy right now, and the focus has to be on that. But I'm going to try to do everything possible to get done with that day a little bit early so we can watch it. As far as it, being on station, it's just going to depend on the orbital dynamics and kind of where it is and where we are as to whether we'll be able to see it or not. I know NASA personnel are working really hard on letting us know if that's going to be the case or not. Because I've just kind of been, knee deep in this training, I don't have a great knowledge of that. But I do know that if it's going to happen, we'll know about it, and hopefully we'll get some amazing pictures from it.
Thank you very much for your time today. Godspeed, sir.
Thank you, Gina. I appreciate it. It was great talking to you.
Good morning, or good evening, I should say. Frank, Bill Harwood, CBS News at the Kennedy Space Center. Thanks so much for taking a moment for me.
Hey, Bill. Yeah, good morning to you. Good afternoon to me here. It's we're almost done with the workday here.
There you go. Just a couple of questions I wanted to run by you that we never got around to at the news conference. You told me a little bit about your two crewmates. I was wondering of your impressions of the Soyuz spacecraft as an operator, as a long-time helicopter pilot. You have a lot of flight experience. What is your sense of the Soyuz, the accommodations, its capabilities, etc.?
Yeah, I think one of the things that you look for as an aviator and as an astronaut, anybody who's going to be in any sort of spacecraft or aircraft, is reliability. And the Soyuz is incredibly well proven. It's got an incredible track record. And from that sense, I feel very safe. It is proven technology in the sense that it's been around for a long time. But because of that, it's just all been pretty tried and true. So, I think if nothing else, I feel very confident that it's a great spacecraft and it's going to get us up there and back safely.
And, one of the things we did talk about a little bit at the news conference, but I'd like to go into it in a little bit more detail, is the importance of the seat swap. Having an American on board a Soyuz routinely and a cosmonaut aboard a U.S. commercial ship routinely, in the sense of, if a crew had to leave, that there'd always be one, each nation would always be represented. Could you talk about that a little bit and what sort of scenarios come into play and how important that is?
Yeah, I think there's two sides to that. Obviously, from the ISS side, I think it is very important that it gives us redundancy and the ability to respond to unforeseen circumstances. So I think from that sense, it's very important. It essentially gives us a backup plan. From the other sense, historically, right, although there's been tensions between our nations, it is important to realize there's a long-standing history of cooperation, right, back from the Apollo-Soyuz program to the Shuttle Mir program, and now 20 plus years of working together on the ISS. And I think it just builds camaraderie and trust in a way that's very important to maintain, especially in moments like this when there are tensions in other aspects. Again, I'm very honored to represent our nation, and I'm proud to be here. And again, I can't emphasize enough how much of a good thing I think this is.
Oh, yeah, no, no question about that. I guess what I was wondering was, to me, it seems like the point of it is to make sure that under any circumstance, there's always at least one Russian on board the station and one American to operate U.S. and Russian segment systems. I'm not misinterpreting that, am I? That is the primary goal of this, isn't it, to ensure that?
Again, I really do feel like it's twofold. That is absolutely part of it, right? Is the fact that it does give us redundancy and a backup plan for both nations, but I do think, the cooperation is equally as important. So I don't want to underemphasize that part of it. But absolutely, I mean, having a backup plan when it comes to something like human spaceflight is absolutely critical.
Well, let me switch gears a little bit here. I was just wondering, obviously you're no stranger and your family's no stranger to deployments, and of course you've done a lot of combat missions and tours. But what do they think about going into space? That seems like a a different level entirely.
Yeah, they're pretty excited, right? I think they appreciate the uniqueness of this opportunity. Certainly, there's absolutely some things to possibly be nervous about, but I'm very blessed that my wife has always been very supportive of that, and because of that, I think my kids have kind of grown up like that in the sense of we worry about the things we can control and try not to worry about the things we can't control, and she's incredibly good at that. And because of that, I feel very comfortable in her support in this whole situation.
I'm no good at guessing ages looking at your face on my television monitor right now. I could look at it in your biography. But how old are your kids? I'm just curious if these are grown kids or you guys still got young ones around.
Yeah, they're kind of on the younger side. Our oldest is 18, a 17-year-old, 14-year-old, and a 12-year-old. So we have 4 teenagers, which makes it a lot of fun.
Oh, yeah, F1 launch coming up puts a lot of focus on the Artemis program and what's going to be accomplished down the road. I was looking for your perspective as a doctor. What are some of the big outstanding questions that need to be resolved before people can travel to Mars? And how do you address that on both ISS and I guess down the road, Artemis missions as well? How are you going to get that knowledge so that, we'll be confident when we send people to Mars, they're going to be able to get there and get back in good shape?
Yeah, sure. It's really pretty neat, right? We do have a presence on Mars already. We have robotic presence there, and we have had for a while. And so bringing humans into the equation for any sort of space mission just complicates things exponentially. And so again, it's, I think like anything else, NASA is going to tackle it step by step. We're just going to focus on the next problem, solving that problem, and while also focusing on the long-term picture. I think the biggest things that are currently the concern, I think, are radiation for sure, right? And I think people always wonder, like, why is that so hard to manage, right? As we do so all the time on submarines. And the problem is just weight. We just can't launch a bunch of iron plates into space to manage that radiation. And so figuring out innovative ways to deal with that problem, I think, is going to be a unique challenge. And then again, just also how our entire systems, primarily the cardiovascular system, the nervous system, how they handle microgravity environments, and not just microgravity environment, but then how you, once you are reintroduced into a partial Earth gravity environment, how do you handle that after essentially being deconditioned, right? What kind of training do you have to do? How do you have to stay prepared? How long do you have to adapt once you get there? Those are all going to be pretty unique challenges. I look forward to contributing to that in whatever way possible, whether it's, as an astronaut that's participating in the mission, or when I'm not flying as a doctor who helps provide ideas and solutions to those problems.
Well, Frank, thank you very much. I'm out of time. Wish you best of luck on your flight. Look forward to talking to you in space.
All right, Bill. Well, it was great talking to you again. And thanks again. Take care.
Okay. Well, Frank or Dr. Rubio, first of all, thank you so much for doing this interview. And how should I refer to you? Frank, Dr. Rubio?
Hey, Kristen. Yeah, Frank would be great. It's great to talk to you.
I'm very excited to talk to you. Thank you so much for taking the time out of your busy training schedule to do this. Well, first things first, you're about to become one of the very few humans to ever go into space, but you've already had quite a unique experience. I mean, you're one of the few Americans right now in Russia during a time of such conflict. What's it been like?
Yeah, it is a privilege to be here. We do actually have a pretty robust NASA team that's here to support the mission, and so I feel very fortunate in that I feel very well supported, and there's a bunch of us here. And I think every one of us would say we do feel safe. Now, we are very focused on the mission. We're in Star City, and we're just trying to get the training done, and as far as being ready for this mission. But the Roscosmos trainers, just like the NASA trainers, take a lot of pride in their human space program. And so I feel very much ready for this mission, well trained, and very supported by them.
Did you ever have any second thoughts about flying on a Russian Soyuz in the middle of this conflict with Ukraine?
Again, not really, because I trust my crew wholeheartedly. And the more time I spend with the trainers and the people that produce the Soyuz rocket and spacecraft, the more I am reminded of the NASA team and just the amount of pride and the amount of caring that they have towards the crew. And so I feel that while I'm here, and so I'm very confident in our mission.
And how about your family? I believe you have a wife and 3 children. Sorry if I don't have that exactly right, but did they ever call you and were they ever like, Dad, what are you doing? Yeah, well, we do have 4 kids, but only 3 at home. So yeah, you got that right. One's off to college now. I think they've been equally as excited about this. If anything, right, there's a little bit of nerves about the whole big picture of going to space for the first time, spending 6 months up there. I don't know that the Russia thing ever became a worry for them, and it's still not. I think we're focused on the mission itself. They've been able to meet my crew. My crew has met my family. And so there's a level of comfort there that I think is really, it's great to have going into this mission. Do you ever speak to your cosmonaut crewmates about what's happening in Ukraine?
Yeah, we've addressed it very shortly, to be honest. And I think it's important to just focus on the mission and develop the trust that we need as a crew. And I don't know that it necessarily would be a problem to talk about it. I feel confident about how I feel about it, and as I'm sure they do. But more than anything, we try to avoid, I think, anything that would take away from our camaraderie and the fact that we're focused on accomplishing this mission safely, supporting each other while we're up there. We're going to have a lot going on. They possibly have 5 spacewalks going. The USOS side has 4 spacewalks going. We're going to have a lot of things coming and going from the space station. And so I think it's critical to have as cohesive a team as possible. We have that going into this. I think we're going to have stronger bonds the more time we're up there. And I look forward to having lifetime friendships with them.
You've been in Russia during a time of, some political change within Roscosmos itself, from Dmitry Rogozin to Yuri Borisov, and then there was some confusion about whether or not Russia was going to pull out of the ISS before 2024. What was your experience like around that? Did you have any concerns as that was going on? And just since this is probably my last question, could you just speak to the importance of, or what you believe the importance to be of continuing this international cooperation at the ISS, which has gone on for so many decades now?
Yeah, so at my level, again, I think I've stayed as focused as possible on the mission. And so I was pretty protected from the higher up issues. I was certainly aware of them, but I didn't really spend a whole lot of time worrying about it, in the sense that it was completely out of my control. And I had so much training to complete, right, because it did take a while to get the agreement in place. And although we were training up for the mission, there's just a certain amount you can't do until the contract is signed. And so it's been pretty busy for the last, 6 months to a year. And so I've really tried to just focus on that and being ready. As far as the crew swap and how important that is, I do think it's incredibly important. It's important to realize and acknowledge the history that we have of working together, despite incredibly challenging times, right? We, throughout the Cold War, we had the Apollo-Soyuz program, then we had the Shuttle Mir program. And then after that, we've been working together on the ISS for 20 plus years. And so I think it's important to remember that. There have been other times where political tensions may have been high, but we've figured out a way to continue working together in a human spaceflight. So yeah, I'm honored to be here. I'm honored to represent our country, and I think this is a good thing that will lead to, in some way, improved relationships between us.
You're now in the running to be one of the Artemis astronauts, fly on one of these missions to the moon. How does that play into your thinking, or are you just focused on this first flight?
Yeah, it doesn't really play into it at all. I do think it's important to stay focused on the mission at hand. Now, what does play into it is knowing that some of my friends will be up there soon. And so that's super exciting. I'm thrilled about that. I'm happy to, get back from the ISS and help contribute to that program in whatever way I can, and hopefully help my friends get up there, and maybe someday get up there myself. So yeah, it's exciting times. As you well know, as NASA tackles new things, it's just an exciting environment to be around.
And finally, you're a physician. Tell me about some of the experiments that you're most excited about conducting up at the ISS.
Yeah, there's so many. I think the one that I'm most excited about is the biofabrication experiment, mostly because I think that has a lot of promise long-term in space, where the microgravity environment is going to allow us to hopefully fabricate human organs and just make a huge difference in the transplant needs that humanity has. So we're going to have that experiment fly up here shortly and get that restarted. And I can't wait to see what steps we make towards eventually making that a reality.
That's so cool. Well, Frank, best of luck. Good luck, Godspeed. And we look forward to watching you launch in a few weeks.
Well, thanks, Kristen. I appreciate it. It was great talking to you.
Great talking to you, too. Bye.
Bye-bye.
Hi, this is Courtney Kuby from NBC News. Colonel Rubio?
Hey, Courtney. This is Frank. I've got you loud and clear. How do you hear me?
I hear you great. Thank you so much for taking the time. I know they've got you sort of on what we in TV call the wheel of death, which is just interview after interview after interview. So
no, it's a lot of fun. It's great to talk to you guys.
Good. Okay. Well, hopefully we will not make this too miserable for you. But I want to start by asking about some of the training that you've been doing. So how long have you been training there in Russia, and how have you seen the training there different from the training that you received in the U.S.?
Yeah, so you normally get assigned to a mission about 2 years out. Because of the different things going on with my mission, I've probably been training for about 1.5 years now. So a little bit of a curtailed timeline, but not by much. And during that time, you travel here to Russia, usually training here for anywhere from 4 to 8 weeks at a time. We also train at the JAXA, the Japanese Japanese Space Agency, and also the European Space Agency. And so we spend a lot of time in those places. We go up to Canada and train with CSA on robotics. And so you're kind of all over the place, getting trained by all these amazing people. I think more than the differences, you really notice the similarities between all of our partners. And that's incredibly talented engineers that truly and deeply care about human space exploration. And you can just see that in the way they pour themselves into your training. And so, it makes you feel honored and pretty blessed to be in the program, because you have all these amazing people putting their time into you. And I think that, without fail, that is absolutely held true at all of the partner agencies.
So I heard during the press conference the other day, you talked a little bit about two of your Russian crew members, Sergei and Dmitry. How would you say your relations are? You're the only American on this crew, right? The rest are all Russians. Is that correct? How would you say that the relationships are working out?
Yeah, so there'll be 3 of us on the Soyuz, but there are 4 other people coming up around the same time on Crew Dragon, right? And so Anya Kikina, another Russian cosmonaut, will be on that crew. We'll have 2 American astronauts there and a JAXA astronaut. So we'll have quite the international crew. And we all get along incredibly well. I've been blessed that to have just a great crew, right? Great people. It makes it a lot of fun, to be honest. And they're also incredibly talented and very capable. And so you also feel very comforted by the fact that you have strong people with you, which makes for an incredibly strong team. And going into it, I feel like we could tackle anything up there. We're going to be busy. And so you're happy to be able to share that load. But again, it's pretty incredible how well we all get along.
Can you explain to me what this seat swapping is that you're going to do? What does that mean?
Yeah, sure. So according to this agreement that was signed, for the next few years, an American astronaut will fly on a Soyuz spacecraft, and a Russian cosmonaut will fly on a Crew Dragon spacecraft, and will essentially be on the ISS pretty much for the most part at the same time. There'll be a couple weeks differences both on launch and on departure. And then once you're up on the ISS, I will work primarily on the USOS side, and Anya will work on the Russian side. But we see each other every day. The entire crew tends to eat together at least once a week. We will often share exercise facilities, and after the workday, you'll go over to their side, they'll come over to our side, and just spend time together.
I know there's a long history between the U.S. in human space exploration between the U.S. and Russia, and I think a lot of people, just given the political tensions that exist right now, would be surprised to know that it's continuing. So, is there, when you're having these group dinners, or when you're maybe working out together, does the current political environment, the war in Ukraine, does that ever come up? Is there any awkwardness with that?
Well, I haven't been there yet, right, to know, to be able to answer that from the ISS perspective. But I will tell you here on the ground, there's really not. We don't talk about it much, and it's not necessarily to avoid the topic. But I think all of us really just focus on the mission at hand, the training, and everything we need to get done to make sure that we're ready for our space flight. There's just a lot. There's a lot to handle as far as the training load. And so I think you spend most of your time and energy putting into that for about 2 years. Leading up to it, we're getting along great. I have full confidence that we're going to get along great once we're on station, and I think be good friends thereafter.
Another thing that I'm kind of struck by is you're in a unique position being in active duty military because you have experience with deployments. Do you think it makes it easier, or you are in a unique position to be away from your family for 6 months because of your background in the military? How do you think that prepares you for this?
Yeah, I don't know that anything ever prepares you for being away from your family. No matter how many times you do it, it's still hard. The good thing is I feel like we do have a strong family. My wife is incredibly capable and strong, and I think she's going to handle things probably better than when I'm around while I'm up there. The other thing, though, is really for the past 25 years, the military and the Army specifically has been focused on kind of the hearts and mind mission, right? So there's been a lot of diplomacy in that time frame that we've worked on relationship building. And so I think that's definitely contributing to my time here at NASA, and it's helped me be a better astronaut and a better person. And I do feel incredibly well prepared for this mission because of my background.
What is the hardest part going into this? What is the hardest part for you personally, the preparation?
I do think it's being away from family. Like I said, that's never easy, right? You are missing a good chunk of time from your kids. You never get that time back. This is unique in the sense that we're all pretty excited about it, right? And so despite the separation, there is an underlying excitement about the mission. And so that makes things easier. Other than that, the academic load, kind of like medical school, it's not necessarily that it's incredibly hard. It's just a lot. And you're trying to, juggle all of these topics and all of this knowledge at the same time and keep fluency in all of it at the same time. And so I think that is probably the biggest challenge, is not necessarily the difficulty, but the quantity that we have to deal with.
What will your family be able to? Will you see them before you leave? Can you? Or?
Yeah. So we do talk regularly, telephonically, and we're able to, FaceTime or Skype or whatever video conference we use. And we are hoping that they will be able to come to Baikonur and see the launch. So that'll be pretty exciting.
That's great. What? We only have another minute or two, but what are you most nervous about going into this?
Yeah, I think just the level of responsibility, right? The funding and the effort that's been put into the ISS up until this point, right? And so you are now partly responsible for this incredible national laboratory while you're up there. Now you have an awesome and incredibly large ground team that supports you. But I think there's just a sense of responsibility while you're up there that you want to do your best and want to make sure that you move things forward and not hurt the mission in any way.
And what are you most excited about?
Yeah, I think there's lots of things. I think the rocket launch, the weightlessness, the learning something new every day, I think that's going to be incredible. You're challenged. I mean, I think people don't really appreciate, and I don't yet, but I will soon, how difficult it is to learn to function in microgravity. And so there's a steep learning curve, and everything from just translating and the fact that any little movement pushes you away from what you're trying to do, to sleeping differently. Using the restroom obviously is something that everybody has curiosity about, but that's a new challenge. And so all those things, as you're learning those things, you're just getting better and better at it for 6 months. And so I think that'll be pretty exciting times. And then once we come home, gosh, the re-entry through the atmosphere, that's going to be pretty incredible too. So yeah, I would say the whole spectrum. I'm like a little kid, I'm pretty excited about it.
That's what. Well, good luck. Be safe. I especially wish you very good luck when you come home to all your.
Courtney, you're breaking up, but thank you so much. I appreciate it.
We're starting in 5 seconds.
Okay.
Amigos, escuchen esto. En menos de 30 días, el astronauta de origen salvadoreño Frank Rubio estará viajando rumbo a la Estación Espacial Internacional. Lo hará en una nave llamada Soyuz junto a 2 cosmonautas rusos. Además, Frank es doctor en medicina, cirujano de vuelo y esta será su primera misión al espacio. Esta mañana somos el primer medio hispano que habla con él en vivo desde Star City en Rusia. ¿Cómo está? Buen día.
Buenos días, Eli. Saludos desde Rusia.
Sí, allí tenemos una diferencia de tiempo, obviamente, porque él está en Rusia, pero vamos a tratar de hacer estas preguntas. Está muy poco, lo decíamos, de hacer su primer viaje espacial. En la historia de la humanidad, menos de 600 personas han tenido ese privilegio de ir al espacio. Uno de ellos eres tú. Yo podría hablarte de lo orgulloso que estamos nosotros, pero quiero saber qué es lo que tú sientes.
Bueno, muchísimas gracias, Eli. Más que todo, uno se siente tan bendecido por tener esta oportunidad. Y es un gran honor estar aquí representando nuestro país y también poder representar a los hispanos. Y de veras que estoy muy emocionado por esta misión.
Y aunque te hayas preparado para esto, hablar de ir al espacio debe dar un vacío en el estómago, ¿sí o no? ¿Cómo te imaginas esa travesía? ¿Te preparas de una forma especial para calmar esos nervios?
Bueno, verdaderamente hasta ahora en día todavía no. Creo que ya estando en el cohete y estar listo para el lanzamiento, creo que claro que va a ser un poco. Pero más que todo uno aprende a enfocarse en la misión y en la preparación. Y gracias a Dios he podido practicar eso mucho en mi otra vida en el ejército, ¿no? Como doctor y también como piloto de helicópteros.
Exactamente, has tenido grandes retos en tu vida. Yo quiero saber qué le dices a esos niños que nos están viendo y los jóvenes que a esa hora de pronto tienen ese deseo, ese sueño como tú de ir al espacio igualmente. ¿Qué puedes decirles?
Bueno, más que todo que sí se puede y que la preparación es increíblemente importante. Hay pocas oportunidades en la vida, pero cuando las hay, es importante estar listo y preparado y hacer lo máximo de esas oportunidades. Pero yo creo que yo puedo servir como buen ejemplo de que cualquier persona lo puede hacer si trabaja a esa meta.
¿Ha sido muy difícil dejar tu casa, irte a Rusia, porque allí fue donde te preparaste? Todo este proceso, ¿cómo lo calificas?
Sí, ha sido un poco difícil estar separado de la familia, pero gracias a Dios todos estamos con una emoción para esta misión, entonces nos ayuda un poco, podemos hablar casi todos los días y eso también ayuda. Pero ahora en día estoy enfocado ya preparándome para los exámenes finales, para alistarnos para el lanzamiento. Entonces he pasado la mayoría de mi tiempo preparándome y estudiando para esos exámenes.
Y qué orgullosos nos sentimos de verdad de lo que estás haciendo. Te agradecemos mucho. Él es el astronauta salvadoreño Frank Rubio. Está con nosotros desde Rusia en Despierta América. Por eso escuchan esos espacios de silencio grandes por el delay que hay. Pero sin duda para nosotros esos espacios son simplemente inflarnos más de orgullo. Es importante que sepan que con este viaje Estados Unidos y Rusia retoman los vuelos con tripulaciones mixtas, una práctica que había dejado de hacerse durante la última década, gracias a el astronauta. Y ahora, bueno, seguimos con
muchas gracias.
Y este universo de inspiración, Raúl, adelante.
Claro que sí, nosotros estamos felices de que está aquí en la casa porque a raíz de la pandemia...
Muchas gracias, Frank, mucha buena suerte. Thank you, Nassau.
Muchas gracias, buen día.
Great, thank you.
Hola, Frank.
Hola, Claudia, buenos días.
Buenos días, ¿cómo estás?
Muy bien, muy bien. Muchas gracias. Bueno, para mí es buenas tardes, estando aquí en Rusia. Pero es un gusto saludarla desde acá.
Claro, buenas tardes. Frank, muchísimas gracias por darnos tu tiempo y hablar con nosotros. Me encantaría escribir esta nota en español para todos nuestros suscriptores en Latinoamérica. Y quería preguntarte entonces, empezar preguntándote un poquito sobre tus raíces salvadoreñas. Entiendo que tu mamá es del Salvador. ¿Podrías contarnos un poco sobre eso? Si tienes más parientes en El Salvador, si ella está allí ahora.
Sí, correctamente, mi mamá es del Salvador y bueno, mi familia entera es del Salvador. Aunque hay muchos que viven en los Estados Unidos, todavía tenemos mucha familia que está en El Salvador. Y para mí es un gran orgullo poder representar no solo nuestro país, los Estados Unidos, pero también el país de mi familia, El Salvador. Es algo que es muy emocionante para mí y para nuestra familia.
Qué bueno. ¿Y has podido ir allí en algún momento? O cómo, bueno, me imagino que estás muy ocupado, pero me preguntabas, ¿o cuándo fue la última vez que estuviste allí?
Bueno, sí, ha sido un poco de tiempo, pero sí, yo crecí ahí, aunque nací en Los Ángeles, pasé los primeros 6 años en El Salvador. Entonces, mi primer tiempo y mis primeras memorias son del Salvador. Y por eso para mí es un gran orgullo poder representar el pueblo salvadoreño.
Qué bueno. Y cuéntame, Frank, yo sé que eres piloto, eres médico. Cuéntanos cómo nació o un poco cómo empezaste a pensar en lo de ser astronauta. ¿Eras uno de estos niños que le preguntan ¿qué quieres ser de mayor, astronauta? ¿O no? ¿Cómo fue la cosa?
Sí, Claudia, sabes, cuando me preguntaban eso, más que todo decía que doctor. No fue hasta después que decidí tratar de hacer esta meta. Y más que todo fue porque me di cuenta de qué grandes las metas de la NASA eran, de explorar los cielos y descubrir nuevas cosas. Y para mí esa siempre ha sido parte de mi personalidad. Siempre me encanta la exploración, aunque sea en las montañas, en el mar, a donde sea. Siempre es algo que para mí es lo mejor. Entonces decidí probar y gracias a Dios pude tener esta oportunidad.
Qué bueno. ¿Cómo te estás preparando? Me imagino que es algo, un entrenamiento duro. ¿Y cuántos días vas a estar en la Estación Espacial Internacional?
Sí, es mucho el entrenamiento, ¿no? Han sido casi 5 años que he estado aquí, los últimos 2 preparándome específicamente para esta misión. Pero de veras que tenemos un equipo grande en la NASA que nos prepara excelentemente para todo lo que vamos a hacer. Estaré ahí un poco más de 6 meses y vamos a tener la oportunidad de hacer varias cosas, incluyendo, si Dios quiere, una caminata espacial, muchos experimentos que esperamos que puedan ayudar a la humanidad. Y por eso que para mí es algo que de veras estar ahí, claro que es increíble estar en el espacio, pero más que todo uno se siente muy orgulloso de hacer cosas que le van a ayudar a la humanidad entera.
Cuando hablas de estos experimentos, ¿a qué te refieres exactamente? Entiendo que hay una parte médica, quizás, y el tema de producir los órganos humanos. ¿Es eso a lo que te refieres o qué esperas conseguir allí?
Sí, bueno, eso claro es uno de los experimentos que vamos a estar haciendo, que de veras para mí es emocionante. Creo que es increíble esa oportunidad y aunque estamos solo en el empiezo de eso, creo que algún día sí será una meta que podamos lograr. Y también se sigue estudiando nuestros cuerpos propios, ¿no? Porque hay cosas que necesitamos saber, cómo la circulación es afectada por la microgravidad y también cómo esos efectos afectan al resto del cuerpo. Entonces uno pasa mucho tiempo estudiando a sí mismo uno al otro, ¿no? Y seguimos poco a poco. Creo que teniendo más y más sabiduría en cómo podemos ayudar a los humanos a llegar a la Luna a tiempo largo y luego en unos cuantos años al Marte.
Quiero preguntarte también sobre... Hello? Sí.
Sí, claro.
Quería preguntarte...
Sí.
Ok, es un tema que obviamente te están preguntando muchos, pero que tengo que hacerte. Vas a ir al espacio con 2 astronautas rusos y sabes obviamente que estos son momentos difíciles en las relaciones de Estados Unidos-Rusia. ¿Cómo os lleváis? ¿Habéis hablado de este tema? ¿Cómo son tus colegas y cómo vas a lidiar con esto?
Bueno, primero Sergey y Dmitry, mis 2 colegas que van a ir en la Soyuz conmigo, son amigos y son increíblemente buenos cosmonautas, ¿no? Los rusos dicen cosmonautas, aunque nosotros decimos astronautas, pero es la misma cosa. Y por eso creo que todos tenemos una gran confianza en nuestro equipo y que juntos la tripulación que vamos a tener va a ser muy fuerte y podemos hacer cualquier misión que nos toque. A términos yo creo que nos tratamos de enfocar más que todo en eso y la misión y no en lo político, porque para nosotros no es algo que vamos a poder afectar ahora en día y es un honor representar nuestros países y hacer esa representación lo máximo que podemos, ¿no? Entonces para nosotros creo que en eso estamos enfocados más que todo.
Gracias. ¿Y puedes contarme también si tu familia, son 6 meses que vas a pasar en el espacio, ellos van a poder, tu mamá quizá desde El Salvador, van a poder ir a Rusia a despedirte, vas a poder verlos, sé que tienes 4 hijos, cuéntame un poquito de esto.
Sí, mi esposa y mis 3 hijos menores van a poder venir a ver el lanzamiento. Mi mamá va a ver el lanzamiento de El Salvador. Pero sí, claro que es una gran cosa para mí poder tener a mis hijos acá. Mi hija mayor, lástimamente, ya estando en la universidad, no puede dejar sus estudios para venir, pero sé que va a estar viendo el lanzamiento en la televisión. Y creo que va a ser una gran experiencia para nosotros.
Claro. ¿Y qué va a ser lo más difícil para ti de este viaje? ¿Qué desafíos crees que son los más duros en una misión así?
Bueno, la separación de la familia, claro que es, creo que para mí especialmente lo más difícil. Físicamente, yo creo que las caminatas espaciales son lo más difícil. Esos son 8 horas que uno está trabajando, muy fuerte y también tiene que estar enfocado increíblemente bien, ¿no? Entonces yo creo que eso va a ser lo más difícil. Además de eso, yo creo que estando 6 meses ahí y saber que cada día cuenta, ¿no? Entonces cada día uno tiene que dar su mejor esfuerzo. Y creo que al final voy a estar un poco cansado, pero muy orgulloso de lo que vamos a poder lograr como un equipo en la estación.
Attention! NASA television programming on Galaxy 13 is moving from transponder 11 to transponder 15. The transmission modulation format is now DVB-S2 8PSK. This move is in line with the Federal Communications Commission's initiative on domestic satellites in support of future 5G terrestrial communications efforts. Transponder 11 and 15 are both active during this transition. Distribution of NASA TV programming on Transponder 11 will end on August 29, 2022. For more information, go to nasa.gov/NASA-TV.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
Hi, I'm Serena Anand-Chancellor. I'm a NASA astronaut, and this is Ask NASA, and I'm ready for your questions. All right, so first question, what is Artemis, or what is the Artemis program? So the Artemis program is our lunar exploration program. We will get to the South Pole of the Moon by 2024, landing the first American woman and the next man. Why are we doing this? Well, in order for us to head towards Mars, we need a special place where we can practice, essentially develop robust engineering technologies, figure out how well the human does with long-duration spaceflight, learn how to build habitats, and we do all of this on the moon. Essentially, we practice. It's an engineering battleground, so we can go to Mars. What do you think it'll be like to go on an Artemis flight? Well, let me tell you, this would actually be really cool to go on an Artemis flight because we'd be heading to the moon. Now, what vehicle will we be traveling in? Well, it's actually the Orion vehicle right here. And some of you may recognize this. This is similar to the old Apollo capsules, but it is bigger, it is better. I've actually climbed inside the mock-ups, seen the systems, very modern systems. This is what will be taking us back to the moon. It's gonna have the first American woman on the moon.
Serena, did you always want to be an astronaut?
I did, probably since I was 8 years old. My dad finally asked me one day, do you want to be an astronaut? And I said, yes.
What one personal item did you take to space?
Oh, I took multiple personal items. It wasn't just one. Funny enough, I took a back scratcher because you need a back scratcher wherever you go.
What food would you take to the moon?
Oh, easy. Cheeseburger, French fries, every time.
Yum. If you were in a dance-off with an alien, what song would you pick?
That's easy. It'd be Michael Jackson's Billie Jean. We played this song on the launch pad.
What do you miss the most about Earth when you're in space?
I missed feeling the Earth. So I miss the wind, I miss the rain, I miss the smell of the Earth, the smell of the grass. These are things you just can't imitate on station.
Is it scary being in space?
It's not scary being in space. I mean, it's your home, and it's the size of a 5-bedroom house. It's absolutely huge, and your friends are up there with you, so what's better than that?
Do you have a question for NASA? Send your questions to our experts on Twitter using hashtag AskNASA.
We are at Kennedy Space Center. Every piece of hardware necessary to return to the moon is now here.
They are being assembled, stacked, fueled, and primed for flight.
The next time these engines fire up, we'll be on the launch pad to send an uncrewed Orion spacecraft around the moon on a flight test for the Artemis 1 mission.
It's been a journey of 1,000 miles from factory floors all across this country and around the world to here. And now the stage has been set.
We are seeing Artemis take her place.
The framework to support the enormity of this moment can't be measured in renovations and rehearsals alone.
But in the testing of a metal found much deeper.
With each segment built upon the one before it, the volume of anticipation can be seen rising.
For in addition to certifying what a host of testing has already previewed,
liftoff. The dawn of Orion and a new era of American space exploration.
Artemis will demonstrate a new path to the moon for this generation.
Artemis 1.
An uncrewed test flight will be a final proving of every system
and every component
in the harshness of space.
A mission that, when successful, will open the door for the moonwalkers and lunar experiments
that so many have hoped and dreamed about.
We are going.
Three, 2, 1, 0. Mission liftoff.
Artemis 1 will lift off from Launch Pad 39B at NASA's Kennedy Space Center in Florida with 8.8 million pounds of thrust, provided by the most powerful rocket in the world, our Space Launch System rocket, or SLS. The uncrewed flight will be the first integrated test of SLS, our new Orion spacecraft, and exploration ground systems at Kennedy. Artemis 1 will send Orion beyond the moon, 280,000 miles from Earth, farther than any human spacecraft has ever flown.
This is not NASA doing this. This is the United States of America doing this program, the Artemis program, and there are companies all across our country that have a part in it, so there is kind of this wave of excitement being generated just by saying, we're going back to the moon.
After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days to perform science experiments and technology demonstrations. Orion will make its multi-day outbound trip to the moon, propelled by a service module provided by the European Space Agency. Engineers will test Orion's systems on the way to the moon. Then, Orion will fly about 60 miles above the lunar surface, using the moon's gravity and engines on the service module to enter a lunar orbit. After about a month and a total distance of over 1 million miles, Orion will return home, faster and hotter than any spacecraft has before. A primary goal of Artemis 1, ensure Orion safely returns to Earth before we fly with humans. When we do, we'll build our capability for sustainable lunar exploration, preparing us for missions farther into the solar system.
Initially, what we'd like to do is start establishing a presence on the moon. So we're going to establish going back there on a regular basis, and then we'll end up setting up Gateway, and we would launch to the Gateway, and from Gateway, land on the surface of the moon.
We are there for, weeks, months on end. And there, we're going to be able to test out all the hardware and the habitats and the hatches and the suits and the rovers that'll allow us to prove out those technologies. The moon will lead the way to Mars, and we should be there within the next couple decades.
We're going to the moon to explore, and we're going to the moon for scientific discovery.
Our destiny is always to go and see what's further and what's next.
The moon is a stepping stone, and the moon is a place we need to learn how to live so that we can continue to go beyond.
We are focused. We are focused on all that lies before us. Only together will we bring to life this global ambition of returning to the moon. And while our work is far from finished, we've never been closer to seeing a new generation step beyond our home planet. We are building on the achievements of those who came before. The giants who conquered gravity and raised a banner in the heavens, they beckon us to go farther, to the moon and on to Mars, to seek a deeper understanding of our universe and bring all that we learn home. 2020 was a year of unpredictable hardships, and yet, step by step, we resolved to press forward toward this grand vision. The daily efforts of thousands of suppliers from all across this country and around the world fed into stunning milestones and laid the groundwork for history.
Launch team, go.
Artemis has been woven into our culture. It has fostered collaboration across the aisles and across the ponds. It has grown beyond plans and preparations to include hardware and software. And now, it has a heartbeat. You can feel the momentum. It is undeniable. We are going. And together, we will see Artemis light the way.
Our mission to the moon is no longer some far-fetched dream. This is reality. We are going.
This is the next step in evolution. They're not just PowerPoint slides. They're actually metals being bent, shaped, formed to build the things that we're going to use.
This is real. This is going to happen. We're going.
We are going to the moon to learn how to live on other planets for the benefit of all.
Let's go.
We are going. The history of this agency is marked with broken barriers, once viewed as impossible, with science fiction turned reality, with innovations that have spun industries all their own, and with demonstrations of peace for all humankind.
We soar in the skies of our home planet. We maintain a human presence just outside of gravity, and we touch points all across the solar system and beyond. We're going back to the moon, and this is why.
The moon is a treasure trove of science.
It holds opportunities for us to make discoveries about our home planet, about our sun,
and about our solar system.
The wealth of knowledge to be gleaned from the moon will inspire a new generation of thought and action.
Without fail, every major program and mission NASA has invested in has led to technologies and capabilities that have shaped our culture.
The breakthroughs of the Artemis era will define our generation and the generations to follow.
The tens of thousands of jobs associated with propelling us to the moon today are just the beginning of a lunar economy that will see hundreds of thousands of new jobs develop around the world.
This is not an ambition of one entity or one country. The exploration of the moon is a shared effort.
Woven together by a desire for the greater good.
Why the moon? Because the missions of tomorrow will be sparked by the accomplishments of the Artemis generation today.
Because the ambition to go has already begun.
And because Mars is calling. We need to learn what it takes to establish a community on another cosmic shore. So let's camp close before pushing out.
And so, we go to the moon now, not as a series of isolated missions, but to build a community on and around the moon capable of proving how to live on other worlds.
We'll use the lessons from more than 50 years of peaceful exploration to send a new generation to the lunar surface to stay.
We will anchor our efforts on the lunar South Pole to establish the Artemis Base Camp,
positioning us for long-term science and exploration of the lunar surface.
We will prove what it takes to assemble a complex ship in deep space.
We will perfect descending down to and returning from a distant surface.
We will learn how humans can survive and thrive in a partial gravity environment.
With improved spacesuit designs, mobile habitats, and with reconnaissance robots pre-positioning and relocating supplies.
We will learn how to utilize the resources we find on these other worlds, starting with finding water ice and purifying it to drinkable water.
And refining that into hydrogen for fuel and oxygen to breathe.
We will establish fission power plants on the surface of the moon, capable of supporting a growing community of efforts.
And we will expand the logistics supply chain to enable commercial and international partners
to resupply and refuel deep space outposts.
None of this is simple or easy, but nothing in our history ever has been.
The Eagle has landed. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
This kind of continuous lunar presence is a natural extension of all that we've learned in low Earth orbit. And what we will accomplish there will ensure the monumental missions to Mars are within reach. As we ready the launch of the first Artemis mission, and as commercial companies ready their lunar landers for the first private payload deliveries, we have already begun to take the next step.
At NASA, we have always answered the innate call to go.
With Artemis,
we are going to stay.
Proving that humanity
can live on the moon,
Mars, and other worlds,
and share the wonders of the solar system with all.
Our story is one of people.
All those who make this journey possible.
From advocates across communities,
to companies across industries,
to countries around the world,
we achieve this collective endeavor.
Our efforts create impact for all.
Technologies that revolutionize industries.
And jobs that bring prosperity to people.
The discoveries from space
benefit the way we live on Earth today.
And those from the moon
will create a better future
for generations to come. But to do that,
we must go.
Hi, I'm Chell Lindgren.
My name is Raja Chari.
Kayla Barron.
Kate Rubens. Hi, I'm Christina Cook.
NASA astronaut Joe Acaba.
Jessica Amir.
Woody Hoberg.
Ann McClain.
Stephanie Wilson.
My name is Johnny Kim.
Nicole Mann.
Victor Glover.
Jessica Watkins.
Hi, I'm Matthew Dominic.
Jasmine Mogbelli.
Frank Rubio.
Scott Tingle.
This is what we do.
This is what we will do.
Let's go.
We go to the moon to learn how to live on other planets.
For the benefit of all.
The move to the launch pad ahead of our Artemis 1 flight test, discussing priorities for national space activities, and cargo and science head home from the space station. A few of the stories to tell you about this week at NASA. On the night of August 16th, teams at our Kennedy Space Center began the approximately 4-mile move of the Space Launch System or SLS rocket and Orion spacecraft from the Vehicle Assembly Building to Launch Pad 39B in preparation for the launch of our uncrewed Artemis 1 flight test. The rocket and spacecraft arrived at the pad the next morning. Artemis 1 is the first in a series of increasingly complex missions to help us establish a long-term presence on the moon. The mission also will serve as a stepping stone to sending astronauts to Mars. Artemis 1 is currently targeted for launch no earlier than August 29th. Vice President Kamala Harris recently met with the National Space Council at the Chabot Space and Science Center in Oakland, California, the official visitor center for our Ames Research Center. Aerospace companies at the event had the opportunity to display and share their work with the Vice President. The Vice President, who serves as the chair of the National Space Council, also made a speech in which she discussed upcoming priorities for national activities in space, including strengthening public-private partnerships and the benefits of space exploration for all. On August 19th, a SpaceX Dragon cargo resupply spacecraft left the International Space Station and headed back to Earth with more than 4,000 pounds of supplies and scientific experiments for NASA and others. This was SpaceX's 25th commercial resupply services mission for NASA. Another asteroid has been added to the to-visit list for our Lucy spacecraft. Lucy's science team recently discovered that the smallest of the mission's Trojan asteroid targets, Ptolemy, has a moon. With this discovery, Lucy is now on track to visit a total of 9 asteroids, 1 main belt asteroid, and 8 so-called Trojan asteroids, a previously unexplored population of asteroids that lead and follow Jupiter in its orbit around the Sun. Our Wallops Flight Facility in Virginia recently helped teams of U.S. college students launch their technology experiments into space. The experiments were launched on a Terrier-improved Malamute sounding rocket to an altitude of about 91 miles before descending back to Earth by parachute. The investigations were flown through the RockSat X program, which gives students the experience of building experiments for spaceflight. A quick note about an upcoming change for NASA television. NASA TV programming on Galaxy 13 domestic satellite is moving from transponder 11 to transponder 15. Currently, both transponders are active, but distribution of NASA TV programming on transponder 11 will end on Monday, August 29th. For complete details, please visit go.nasa.gov/transponder. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan. Attention! NASA television programming on Galaxy 13 is moving from transponder 11 to transponder 15. The transmission modulation format is now DVB-S2 8PSK. This move is in line with the Federal Communications Commission's initiative to free up C-band bandwidth on domestic satellites in support of future 5G terrestrial communications efforts. Transponder 11 and 15 are both active during this transition. Distribution of NASA TV programming on transponder 11 will end on August 29, 2022. For more information, go to nasa.gov/NASATV.
Exploring the universe is a daunting task. There are often immense challenges that must be overcome before even setting out on a mission. The Ionospheric Connection Explorer, or ICON, has faced multiple barriers that have delayed its journey to study the frontier of space, the dynamic zone high in our atmosphere, where Earth's weather meets space weather. But before we can reap the benefits of its scientific research, ICON must launch successfully. The ICON team's can-do spirit will be repeatedly pushed to its limits while striving for a long-awaited and hard-earned T0.
A successful space launch requires flawless execution of a highly complex machine, and Pegasus Icon is no different. During previous attempts, we observed some anomalous readings. We worked through that with NASA and implemented corrective actions. This will ensure a highly successful mission.
Perseverance is doing something despite difficulty or delay in achieving success. It's a required virtue when the subject is spaceflight and the focus is a successful mission.
Just like any rocket, you have your share of problems that you run into, because this is rocket science after all.
Issues arose, but dedication never wavered. The entire Icon team knew this was about more than just rocket science. It was about the payload, science that would benefit all of humanity. As with every NASA program, giving up is never an option.
It has taken us months, hours, days to really resolve a lot of these issues with this integrated team. And thankfully, we were able to get through them, and here we are, getting ready to launch.
The ionosphere is not only the area through which radio communications and GPS signals travel, it's also the space where many critical satellites and spacecraft orbit, including the space station that houses our astronauts. But despite the importance of this region, it is not well known. That's why NASA and the University of California, Berkeley built ICON.
The ionosphere itself, where ICON will be doing most of its work, is where the GPS signals travel through, it's where astronauts travel, and so it's very, very key for us to understand this region because it has profound effects on us here on Earth because of what space weather is doing to us, but it also gets profound effects of what our Earth weather is doing to the ionosphere.
By studying how the ionosphere reacts to Earth's atmosphere, it will help scientists and meteorologists forecast the conditions in our space environment, reducing its negative effects on our technology. From 360 miles above Earth, at a 27-degree inclination, ICON will sample ionospheric variations in the lower boundaries of space over the course of hours, days, seasons, and decades. Traveling at more than 4 miles per second, or about 30 times faster than a commercial airliner, this satellite will examine how the ionosphere reacts to our planet's weather.
The ionosphere is highly variable, more variable than we ever expected. Now we think that the answer to understanding the conditions in the ionosphere and being able to predict those conditions relies on our ability to understand how weather below is forcing space weather above. So ICON's built to capture all the information that we think we need to understand the mechanisms and the process by which our lower atmosphere affects our upper atmosphere.
ICON will be sent into orbit by a Northrop Grumman Pegasus XL air-launched rocket. The rocket has 3 solid propellant stages and can deploy satellites weighing up to 1,000 pounds into low Earth orbit.
We selected the Pegasus XL launch vehicle. It provided an excellent combination of mission performance and flexibility for the mission design for a spacecraft of the mass of ICON.
The launch of ICON will be anything but ordinary. It will be carried on the underbelly of Northrop Grumman's L-1011 Stargazer aircraft, a launch pad far above the clouds in the sky.
The one unique thing about Pegasus is that it's air-launched. So the L-1011, which is the last flying plane of its kind, it is essentially our launch pad in the air. It's a mobile launch pad that flies up to about 40,000 feet, and that's where we launch the Pegasus from.
With the tireless effort by the team to reach mission success, it is time for ICON to prepare for another launch attempt.
There are no constraints on the...
For all involved, this is familiar territory, yet something feels different this time.
It's taking a little extra time and extra care with the launch vehicle, but we're about there.
What I'm excited right now is that we're getting so close to launch, and it has taken a huge effort to get there.
Vandenberg Air Force Base in California is bustling with activity. The excitement is palpable as ICON literally comes together. Pegasus stages 1, 2, and 3 are assembled. The aft, skirt, and fin installation are now complete. ICON's solar array illumination is tested. And finally, the spacecraft is mated to Pegasus.
Once it's mated to the rocket, there'll be a compatibility test between the rocket and the observatory. So the rocket will be the interface to communicate to ICON, so we can command it. Once we certify that, we will encapsulate it. We'll put it on a transport platform, roll it out to the hot pad, and then integrate it to the L1011.
Now that processing and mating are complete, the ICON mission takes off from Vandenberg. Hours later, it arrives at Cape Canaveral Air Force Station skid strip in Florida. Important logistics must be coordinated with the 45th Space Wing prior to launch. Once in Florida, there is a week of processing and testing prior to launch day. Lieutenant Samantha Parr is in charge of making sure ICON launches into a safe environment.
So I keep track of the weather, I keep track of our instrumentation, and I keep track of our surveillance. And I provide a recommendation to our launch decision authority, and he or she can make a determination on whether or not we're clear to launch.
We are now at launch day. The team has been here before, and optimism is guarded.
It's been a lot of work to get here. At this point, we kind of see the end, and we're looking forward to a mission and putting the satellite into orbit and seeing what that science does in the future.
Anticipation builds to a fever pitch. All systems are now go for launch.
The actual time parameters for a launch of a Pegasus mission is much different than your standard ground-based missile launch. That's tied to the fact that the Pegasus literally has a first stage by being on an airplane. The airplane's at 40,000 feet, it's moving close to 500 miles an hour. It's moving, you can't stop it, you can't slow it down, it is going and it's dynamic.
The Stargazer jet takes off from the skid strip at the Cape Canaveral Air Force Station.
L1011 is airborne at this time.
The L1011 has now reached a cruising altitude of 40,000 feet and has begun flying in a racetrack pattern.
We fly a pattern called the racetrack. It's an oval in the sky, and so the airplane takes off, flies through the launch point at a lower altitude as it's climbing to the point we're going to launch at, which is roughly 40,000 feet.
We verify that all of our GPS are synchronized and ensure that we are going to put the launch vehicle in the correct heading so that we get the spacecraft into the correct orbit.
LC PEG, go for fin pin retract. LPO, go for fin pin retract and fin sweep.
LC, Senior MEVCO countdown, L1011 is in the box.
About 50 miles offshore at Daytona Beach, the Pegasus XL is released from the L1011.
With the countdown, we hear drop on my mark, 3, 2, 1, drop. And we push a button in the cockpit. The hydraulic releases actually release the rocket.
Pegasus away.
The rocket drops for 5 seconds, the airplane climbs for 5 seconds, and at the end we have a fairly good safety margin.
5 seconds later, the Pegasus rocket ignites.
Stage 1 ignition has been confirmed.
That's the minute that I consider T0 for me.
Soon after Pegasus ignites, first stage booster burnout and separation occurs.
Stage 1 separation confirmed. Stage 2 ignition has been confirmed and attitude is nominal.
Followed by fairing separation and second stage separation.
Fairing deployment has been confirmed.
After third stage separation, the ICON satellite is deployed into its lower Earth orbit.
Spacecraft separation from the Pegasus launch vehicle. So thank you, old friend, for doing that, and good luck, ICON.
It is a monumental moment for the entire ICON team, who banded together to overcome hurdle after hurdle. Powered by teamwork and unwavering dedication to its mission, ICON has overcome all obstacles in its path on the way to a successful T0.
Well, it's been quite a ride. It's been an incredible journey to get to this point and required the sacrifice of a very large team. We couldn't be more excited and honored to have launched the Icon spacecraft in orbit.
Great job for the team. Congratulations, Icon.
Status check to proceed with terminal count.
There is a moment at the start of every mission when everything comes together. A moment when years of preparation and planning are put to the test.
Clear to proceed.
There are no second chances.
You have permission to launch.
Success or failure is just a heartbeat away.
Rocket report range status. Range green.
A spacecraft and its rocket on the pad, fully fueled and ready to launch.
Status check. Go Delta.
In that moment, a controlled explosion is released with such intense power, it can propel a spacecraft off the Earth and into space for the benefit of all. We call this moment T0. This is its story.
To shed light on the mysteries of our closest star, the Sun.
The Sun, the heart of our solar system. It's as familiar as anything we know. Although the Sun has been studied for millennia, it still holds unsolved mysteries about its effects on our daily lives. To better understand the Sun, NASA is preparing to launch a spacecraft called the Parker Solar Probe. It will lift off from Cape Canaveral Air Force Station near the agency's Kennedy Space Center, located in Florida. It's a mission of unprecedented opportunities that could revolutionize our understanding of our star and the Sun's atmosphere, the corona, a long-time destination goal for scientists such as Dr. Nikki Fox.
Going into the Sun's corona for the first time, going up close and personal with our star, to be able to answer some of the mysteries that live in this coronal region. Why is the Sun's corona hotter than the surface of the Sun? Why is there a solar wind? Why does this atmosphere, this corona, become so energized that it can move away from the Sun at supersonic speeds and bathe all of the planets?
And now that Parker has finally arrived on the Space Coast, we're one step closer to solving those mysteries. Delivered on an Air Force C-17, it's not every day this crew hauls a payload destined for the history books.
Overall, the mission itself is relatively simple. I'd say the biggest challenge is probably the load portion.
A little extra to it too, because normally we're just hauling generic things, but not a $1.5 billion solar probe.
And there's only one world-class program that specializes in missions of this caliber, NASA's Launch Services Program, a team that matches the industry's top-performing rockets with the cutting-edge spacecraft NASA is committed to launching.
LSP is NASA's bridge to space. Basically what we do is we link a spacecraft customer such as the Parker Solar Probe up with a launch vehicle provider such as United Launch Alliance. And we provide them with a custom-built ride to space on a carefully selected launch vehicle.
Engineers and scientists with Astrotech and the Applied Physics Lab teams will spend its last few months checking and testing every element and completing final assembly to be sure it is ready to leave Earth for its epic trip to the Sun. Parker must be perfect before T0 arrives.
Before we start integration with the launch vehicle, we have to do final integration of the spacecraft. That includes attaching the magnetometer boom and magnetometers. We'll then also integrate the solar arrays. And then finally, right before integration with the launch vehicle, we'll add the thermal protection system or thermal shield.
The Parker Solar Probe will be the first mission to kiss the Sun, flying through the searing heat of the Sun's corona, traveling closer to the surface than any other spacecraft before. And to do that, it will need to go faster than any other spacecraft in history. That's why, for the first time ever, NASA's Launch Services Program selected the United Launch Alliance Delta IV Heavy rocket.
Parker Solar Probe will be the fastest human-made object ever. We are traveling at an unbelievable 430,000 miles per hour.
NASA selected Delta IV Heavy for the Parker Solar Probe mission because of the combined energy of the booster
delta cryogenic second stage and the third stage, which means that we have enough energy to go to the sun.
I mean, if you look at the vehicle, it's huge. It's approximately 50 feet wide, 170 feet long, and about 190,000 pounds.
Going out and seeing the Delta IV Heavy on the pad is a truly awe-inspiring experience. Just seeing that amount of raw power right in front of you is just incredible. 3 boosters, our second stage, and then we have a third stage. We're a tiny little spacecraft. We look like a little hood ornament on the top of the Delta IV.
Throughout its 7-year mission, NASA's Parker Solar Probe will swoop through the sun's atmosphere, carrying more than scientific instruments on this historic journey to the center of our solar system. It will also hold a piece of humanity itself. Back in March 2018, the public was invited to submit their names. Over 1 million were loaded into a memory card and mounted on a plaque bearing a dedication to the mission's namesake. Dr. Eugene Parker was a heliophysicist ahead of his time. He proposed this mission back in 1958 after discovering the existence of the dangerous and unpredictable solar wind.
The reason it has taken us 60 years to be able to fly this mission is not because we weren't interested. It really is because it has taken that long for technology to be developed to allow us to do this incredible mission.
During the Parker Solar Probe's perilous dive into the sun's corona, the atmosphere, it will navigate dangers never before experienced by a NASA deep space mission. 3 million-degree plasma, sporadic solar flares, and delayed communication with Earth. Traveling this close is only possible because of the spacecraft's protective heat shield, the single largest piece of hardware and the most critical to mission success. One slight error in its performance could cause the probe to melt and the mission would be lost.
Parker Solar Probe is actually going and touching the sun. When we actually get to our closest approach, the heat shield on Parker Solar Probe will be at about 2,500 degrees Fahrenheit on the front surface. The back surface is going to be at about 600 degrees Fahrenheit, but then the spacecraft bus will just be operating at a normal room temperature almost. It's a little bit higher, about 85 degrees. The previous missions have been really important for solar science as we study from afar, and we can learn a lot from studying from afar. But the Parker Solar Probe is actually going and touching, almost kissing the sun, so we can learn so much more.
The spacecraft is now ready for flight, but it can't get millions of miles to the sun unless it gets a boost from a specially made third stage by Northrop Grumman.
The Northrop Grumman third stage team specifically designed and built this third stage for the Parker Solar Probe mission. The Parker Solar Probe needs a third stage because even though the Delta IV Heavy is an incredibly powerful rocket, the third stage is what gets it the extra boost to get into its final orbit around Venus and to the sun.
Parker Solar Probe is the hardest trajectory that I've ever worked on for a couple of different reasons. One, we're flying on the Delta IV Heavy, which is the largest and most complex rocket that Launch Services Program has ever been involved with. And in addition to that, we're flying a third stage that has its own guidance, navigation, and control system on board. So from a trajectory, GNC standpoint, it's like flying 2 missions at once. Parker Solar Probe it's called a heliocentric orbit, which means it's orbiting around the sun. And using a gravity assist, usually we use that to add energy to the spacecraft's orbit when we go out to places like Jupiter or Saturn or Pluto. In this case, we're going in the opposite direction. We're heading inside the orbit of Mercury. The folks at Applied Physics Lab have come up with a very unique trajectory where the spacecraft is going to use the mass of Venus to slow themselves down. And not only are they doing that one time, they're actually going to do that 7 times in a row over a space of 6 years in order to get the spacecraft perihelion, because we're orbiting the sun, down below 10 solar radii. So when we're in orbit around an object, whether it's the Earth or the sun, we go fastest when we're closest to that object and slowest when we get to the top of this orbit. And therefore, when we pass very close to the sun, which is the most massive object in our solar system, we're going approximately 430,000 miles per hour relative to the sun. This really is rocket science.
During the early stages of launch, the Parker Solar Probe will be encapsulated in a large payload fairing. The Delta IV Heavy is a massive rocket designed to launch a school bus-sized spacecraft. The last step at Astrotech is safely securing the 1,510-pound spacecraft in a fairing that, by comparison, makes the probe look small.
To get to the sun, we actually need a lot of energy. Because of that, we need a very large launch vehicle. And in fact, we have the biggest launch vehicle we can get. And because of that, this fairing that is associated with this launch vehicle is very large. But because we're a small spacecraft, we take up a very small amount of space in that fairing. And that's the reason why it looks like we're a very small spacecraft on a very large vehicle. But once the spacecraft is encapsulated, that's it. We no longer get to touch it.
The encapsulated probe is now ready for a slow, steady ride to the launch pad at Cape Canaveral. It will be transported atop a K-Mag made for transporting special payloads. It can hold thousands of pounds, spin 360 degrees, and keep its payload level when traveling up inclines.
One of the nice parts about the K-Mag that we have is it has very precise steering capabilities, and it also has a lot of different steering capabilities. So it gives us a lot of capability to get into a precise location, both for hoisting operations down in the hoistway, as well as different mating operations in our horizontal integration facility.
Now, the ULA team will carefully lift the Parker Solar Probe safely nestled inside its payload fairing to mate it atop the massive Delta IV rocket. To keep the payload safe during the entire lifting operation, there's a special channel constructed in the tower itself known as the hoistway that allows the payload to be lifted without any influence from adverse weather or environmental conditions.
The exciting part about today is it's when we finally get the customer out here, we get the spacecraft hoisted, and that's what it's all been about. A heavy mission by itself is always exciting, but then you add in the factor of having a NASA exploration mission, the mission to touch the sun. That accompanied with the heavy, it's just an exciting launch for the public, a great exciting launch for ULA. It'll be a lot of fun to see, and it'll be a lot of fun to track over the next several years as it gets into its final orbit around the sun.
NASA's Launch Services Program has now brought together the payload and its ride to space. After taking different roads to the launch pad, finally the spacecraft and the vehicle are together.
Goddard runs all of the Living with a Star missions, and this is what's called a flagship mission. It's one of the most important things that our science does. So the anticipation of launch is just tremendous. I've been working on this project for 10 years, and now to see it actually ready to go is just a tremendous feeling. It's really hard to describe.
Now, as T0 is just days away, it's up to ULA and LSP to make sure they're operating as one. In the hours before liftoff, the mobile service tower gantry rolls back, leaving the mighty Delta IV standing on its own, ready for launch. The final countdown to T0 is underway.
As the NASA launch director, ultimately what I do is give the go or the no-go. That's a very simple statement, but there's a lot that goes behind that. It's a culmination of a bunch of professionals that know their jobs, they know it well, and all I have to do is make sure all those pieces are in place. Then it's easy for me to make the decision to launch.
Thousands of rockets have launched from Florida's Space Coast, but this is the first designed to fly to the sun. Big Delta IV Heavy rocket is ready to roar to life with more than 2 million pounds of thrust to power the Parker Solar Probe on a trajectory of millions of miles to its destination.
Proceed with terminal count. First stage systems. Propulsion. Go. Hydraulics. Go. Locks. Go. Launch director. You have permission to launch. Status check. Go Delta. Go PSP.
3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
Look good in the full thrust mode. Response looks good. trajectory looking good right down the middle of the racetrack.
I am gay. I am my authentic self.
I am a queer woman.
I am a transgender woman.
I am a lesbian.
I am gay and I'm my authentic self.
I'm a parent of a transgender son and I'm very proud.
I knew I wanted to be in science ever since I was a little kid. I felt that it was really important to be my most authentic self, especially knowing that this was my dream. Queer people can dream big.
Exploration needs to be for everybody. Every person, every kid, if they can see themselves, the astronauts that we send out in space, but also in the teams that make that possible, then we're doing our job. We're doing incredibly difficult and complicated things. We want people that look at things from a different perspective, that can bring us, new ways of solving problems, and diverse and inclusive teams do that.
If someone is in the closet and they see people like me doing our jobs, being effective at our jobs, I think that is the biggest encouragement that I can give them, is to show I can be my true self and I can do my job. They accept me 100%. We're all together working on this.
Who I am is enough. And when you resonate that kind of pride within yourself and then you exude the love that you have for yourself, before you know it, you've got a tribe of people who are just motivating and uplifting one another. That comes from being your authentic self. There's someone in the world struggling like you who needs to see someone like you to keep going. There's someone who needs an example, and you can be that.
I am non-binary. I am gay. I use they, them. There was one instance where I was participating in a candidate lunch, and they actually also used they, them pronouns. And it just felt really nice to see someone else in the room using those pronouns, and I made sure to introduce myself with my pronouns so that they could know, you're not the only one here. There's someone here who understands you and really just wants the best for you.
It requires some bravery, but take the leap. Just be honest, be yourself. And if you are yourself and they accept you, then you've found what you need. I've learned how to be confident myself, and I've also sort of established myself here. People know me. I get to work with smart and capable people, and our job is to explore outer space and to uncover the mysteries of the solar system as a daily matter. That's what we do each day.
I feel hopeful for the future because of the education that's out there and employee resource groups that NASA has established. I am my true self, in love with my wife. And if we can be ourselves, our mission here at NASA becomes more effective.
We're all different, and we should all accept each other for our differences, because that's what makes us special.
It's really important that we can show that visibility is safe. And that you can absolutely be a part of the team and loved and valued for who you are.
It's never too late to be yourself. It's never too late to find your happiness.
No matter what your identity is in the community, that there's going to be a place for you, and there's going to be a place for you to not only just be here, but to succeed and to thrive. I am a queer woman, and I am NASA.
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 Welcome to NASA Edge.
An inside and outside look at all things NASA.
I tell you what, Blair, we have a great and exciting show today. We're talking about navigation Doppler LiDAR.
And joining us later on the show is our good friend Franklin, who's been busy shooting footage of the test being done with NDL.
But first up, we have my former boss. So we have to make sure we're in good standings.
Yes.
We have Walt England, who is now the Deputy Associate Administrator for Programs in the Space Technology Mission Directorate. How you doing, Walt?
I'm doing great, Chris. Good to be back.
Now, in case for some of the people who don't know, we have this really cool new program at NASA called Artemis. Can you kind of share what that's all about?
Yeah, we're really excited about Artemis. Artemis is the program that's going to take us back to the moon, the first woman and the next American man to set foot on the moon in 2024. We've been investing in capabilities, the SLS rocket, the Orion spacecraft, standing up the gateway, which will truly be the gateway to the moon and points beyond. And the next step is to develop the human landing system, which will take astronauts down to the surface of the moon. And part of that landing system requires technologies to include precision landing and navigation Doppler LiDAR.
So being in the Space Technology Mission Director, what are some of the suites of technologies that you're working on?
Well, we're developing in a whole host of technologies, both robotic technologies for robotic landers and for the human landers that will follow. Solar electric power, nuclear power systems, cryogenic fluid management, precision landing and hazard avoidance technologies, which will enable the human landing systems to get to very precise locations where we're aggregating assets, both robotic and for human exploration.
How challenging is it to develop not only the new technology or develop the landers themselves, but concurrently test all these new technologies that have to work in a complementary fashion with Artemis?
It's a great question, and we're doing that with a very deliberate plan. We're using both robotic systems, small robotic landers, medium-class robotic landers, and eventually the big full-scale human landers. And we need to do those in parallel so that by 2024, all the technologies, all the capabilities will be available and ready to fly astronauts to the surface of the moon.
EDL, entry, descent, and landing, has always been an integral part, an important part of discovering another world or learning more about other worlds. Is that just as important as landing on the lunar surface? Because it really doesn't have an atmosphere compared to the Martian surface?
Well, the Martian surface is actually harder to get to because it does have an atmosphere. Right. But we are using the moon as a proving ground, essentially. The Doppler LiDAR, the precision landing technologies that we need to get astronauts to the surface of Mars, which is the end game. We want to demonstrate on the moon and then understand how they perform and what we need to do to extend those to the Mars surface.
And so that means, for example, when this technology matures as it's actually deployed, it'll probably fly on missions prior to that, and we'll see test data and verify all that functionality even ahead of the astronauts arriving.
Absolutely. There are things we can do with Doppler LiDAR on the ground here on Earth to develop it and prove its capabilities, and we are doing that as we speak. We can do it on the ground or with aircraft or suborbital launch vehicles. We're going to fly the Doppler LiDAR on a Blue Origin New Shepard next year, and then we're going to take the Doppler LiDAR on 2 small robotic landers and demonstrate it at the moon in a fully autonomous sense before we put it on the system that's going to carry the astronauts down to the surface.
I understand there's a project called SPLICE, and that's where you have the hazard avoidance, the navigation Doppler LiDAR, and all the sensors that are part of this program?
Right. SPLICE has a number of different precision landing technologies, including terrain relative navigation, which we actually use on Earth here, but you use cameras to define waypoints and understand visually where you are. We don't have a GPS network at the moon, so we need other ways of navigating down to the surface. We've got a hazard detection capability, so when you get close to the surface, you want to be able to look and see where the rocks and slopes and even craters are and avoid those. You may remember Neil Armstrong and Apollo 11. He was literally within about 30 seconds of running out of fuel because they flew over a big crater and he didn't want to set the lander down in the crater. So we want to do that. We want to be able to do that autonomously with the hazard avoidance technologies, and then obviously the Doppler LiDAR. And the Doppler LiDAR is really about precision guidance, velocimetry, and position. So with radar systems, we get position, and you have to derive the velocity and rates of the spacecraft. But the Doppler LiDAR gives us a much more precise laser-based capability to pinpoint the landing site and understand your velocity and rates and your position as you get near the surface. And I'll tell you, the beauty of the NDL technology is it has tremendous potential for Earth applications as well. So we're developing it for this very specific spacecraft human landing system, but it has applications here on Earth, potentially to drive autonomous cars with aircraft, marine applications. It has a really broad base spin-off capability that people are looking at very seriously.
Now, I know that doesn't drive what we do, but that's got to be really a good feeling, especially on the engineering and science standpoint, to make these breakthroughs meet your objectives, but then at the same time actually open up opportunity for a whole host of different applications.
And that's actually always been part of NASA's mission, not necessarily explicitly, but if you look at all the spin-off technologies that we've developed that we use here in our daily lives at Earth, it's a tremendous investment. And this is probably one more in that long list of things that you'll see in the, in our daily lives.
Well, speaking of NDL, you had a chance to learn more about it.
Absolutely. I had a chance to sit down with Farzin, the principal investigator for navigation Doppler LiDAR, and talk to him about the specifics of how it works. Farzin, navigation Doppler LiDAR. When I hear the word Doppler, I think of like weather radar. How is that different for navigation Doppler LiDAR?
Well, it actually uses the same principles that are used in weather radars. They call them Doppler, right, because it uses the Doppler effect. And the Doppler effect is essentially when an object is moving, it causes a shift in the frequency or change in the frequency of the radiation. In our case, we have a laser radiation. And on the vehicle, when we're traveling, we are shining the laser beam to the ground. And as we are moving, it causes a Doppler shift. And from that, we can get the velocity of the vehicle. This sensor also uses the same laser beam to get the position or the distance to the ground. And by transmitting multiple beams, in our case, we do 3 beams, we can actually figure out what the direction the vehicle is traveling.
But of course, in this case, you're using LiDAR. So how does the NDL actually work?
Okay, the NDL in general provides position, speed, and direction of motion. These are the parameters you need for navigating. You use that when you drive your car, right? You use your GPS and your speedometer on the car. So it's just the same type of things. Now, of course, when we go to other planets or we go to the moon, there are no GPS. So we have to have an onboard sensor to give us position and velocity information. And that's what this system does.
I understand that most of the time we do this using radar, but this offers some advantages.
That's true. You mentioned weather radars. The radars are also used on vehicles, space vehicles in particular, to measure the same type of parameters, position, velocity, your speed, and the direction you are traveling. However, laser provides significant advantage over radar. Being a much higher frequency means that it's more precise. The radar diverges, and the laser beams are pencil beams. That mitigates a lot of issues that inherent with radar system. So it's both precision and data quality that this provides.
And this makes a lot of sense with spacecraft, because as you said, we're going to be going to other moons, planets, types of surfaces that we're not already very familiar with. Was that part of the thinking when you started developing this technology?
Well, when we started, actually, the reason was that when we were talking to the engineers who are building these vehicles to go to Mars and other places, we hear a lot of complaints about the performance of the radars. So that triggers for us to start looking at alternatives, and using laser was an obvious choice. So that's how we got started. And so throughout this development, of course, we are working with those engineers in order to come up with the best optimum design that we could. And that's kind of the process that we went through.
When it comes to the moon and perhaps Mars, do you have to do anything different with the system to handle different atmospheres or anything, or is this a one-size-fits-all kind of system?
Well, as we are developing these for space, we try to envelope all the applications, so we don't have to make design changes from going from Moon to Mars. So we try to design it such that the same sensor system that can be used for both application or other places in the solar system.
So as we prepare with Artemis to go to the moon, where are you guys in the development timeline? I mean, do you have a working model? What's the status?
Yes, we are working on a working model right now. It's almost done. So the first engineering units are going to be demonstrated on 2 commercial landing missions in 2021. So throughout this, we are going to be keep improving it, making it more robust. So for the Artemis, we'll be hold out more reliable to ensure that the mission is successful.
And that's really interesting too, because by flying on these commercial missions, you're actually getting flight performance and actual real data to help iterate the system.
Absolutely, this is quite a luxury for us because normally when NASA develops systems, they go through a bunch of tests, in the laboratories, doing vibrations, they put them in a vacuum, they run them over different temperature, they radiate them. You go through all of those, and you still have a little bit of a discomfort when you go to the space. Having this demonstration is extremely helpful to us as a developer, and it's also helpful to the engineers that they will have more confidence in these sensors. They will have all this data, they know exactly how it's going to perform. So it's a quite valuable experiment.
And joining us back now in the studio is Franklin Fitzgerald. And Franklin, you actually had a chance to spend time with Farzin and the team over the past several months shooting B-roll and covering a lot of the tests. Tell us about that experience.
Yeah, Chris, several months ago, we got a call, and they started talking about, hey, we're going to be putting this together. And we actually went over to their laboratory where they were assembling the NDL, the box that we keep talking about, the small suitcase box.
That's the engineering unit that they're building right now.
Absolutely. And after it was assembled, they said, hey, we're going to be putting together several more boxes. But the one that they completed, they started to do testing on it, like vacuum testing and thermal testing. And I documented that at some of the laboratories here at Langley. But the third test that they called me for was the test that they did at the Langley Air Force Base, where they used the lasers that we have here, models on our table, to shoot a target down the runway in the back of an open cargo van. Yeah, I know.
They improvise, right?
Yes, they improvise. But the van was so far away, I couldn't even see the cargo van with my naked eye, but when I looked through my telephoto lens of my camera, you could see it, and you could see what they call atmospheric turbulence,
yes,
or what looks like heat coming off the surface.
Like a mirage.
Exactly. And Farzin told me that as the lander approaches the surface, you have atmospheric turbulence, but the lasers can work through that to get an accurate location and land like it's supposed to.
And with all these tests, Franklin, I mean, you guys would call them up and they seem to be working constantly on this project.
It felt like it was around the clock. And in one test in particular, the vacuum test, I called Farzin. I say, Farzin, are you going to be available at 10 o'clock this morning? He said, I'll be available at 10 o'clock this morning, 10 o'clock tonight. You can come at 3 o'clock in the morning. We're going to be doing a round-the-clock test for the next couple of days in the vacuum chamber. So there were technicians working around the clock.
We know it's important because this NDL unit is going to be going on 2 CLPS landers, in a year or so. So they have to be ready. So they have to be working around the clock to get it ready.
Around the clock.
And I think that's interesting too, because a lot of times we hear about the technology, we see it demonstrated, and you forget about the actual hours that it takes by not just 1 and 2 people, but a whole team to get this testing done so it's ready to fly.
They haven't been working on NDL just for a couple of years. This has been a long process. I mean, they've been going back to the pre-2008 working on this. And I had a chance to sit down with Glenn Hines, who is the chief engineer for NDL, and he talked about that history. Hey, Glenn, thank you for being on the show today to talk about NDL. We've been trying to get you on the show for the past 13 plus years. Glad to have you.
Well, thank you so much for having me.
Farzin did a great job talking about NDL. What I want to do is kind of look at the timeline. Let's take us back to the beginning. And to do that, I got a little cheat sheet here. Of course, I had to have on my little board here. Starting back, in 2008, when you started this project, tell us,
yeah,
how did it get started?
So actually, the project started a little bit before 2008.
Okay.
Farzin's ideas and vision of this particular instrument. But our first helicopter flight of it was in 2008, and that was out in the desert. We worked that project with JPL. It was a huge system at the time. It was, like, say, the size of a refrigerator.
Okay.
And then we eventually flew it on the Erickson Sky Crane in 2010.
That's huge. That's a big box.
Yeah, and it was a very difficult environment to fly in. There was a lot of vibration on the Erickson Sky Crane. And it was still big. It was around 60 kilograms at the time, the size of about a half a refrigerator.
Okay.
But then we started miniaturizing it. We built it to what we call our Gen 2 system and dropped the weight down from 60 kilograms down to about 28 kilograms and made it the size of a rack mount unit.
Okay.
We flew that on some helicopter tests and did some successful flights. And then eventually we flew that same box on the Morpheus vehicle in 2014.
Okay.
And we flew that at the Kennedy Space Flight Center. And it was working in closed loop at the time with the other systems on board. What that means is the vehicle took off by itself autonomously, picked out a safe spot to land, and found that, and then autonomously flew down to a hazard field that we had built down at the end of the runway, and the vehicle landed there all by itself.
So this was the first test of the system.
Yes.
In a sort of a simulated lunar landing environment.
Exactly. This was a progression of moving the instrument from being huge to being small enough to be able to fly to support these landing systems. And these tests proved out not only its capability, but it proved that we could also do the engineering to make it small enough to fit on vehicles. And we made it one more incremental step after the Morpheus flight. We made it into the size of a toaster. Effectively, that's what we called our Gen 3 unit. And we flew that on the Maston vehicle back in 2017. And that's leading us up to what we're building now, what we call the engineering test unit. We're going to make it robust and resilient enough to work in space.
So what would you say, if you take us back to 2008 and beyond, what was probably the biggest engineering challenge that you had to face during that time?
The biggest engineering challenge was the size of the box, getting it small. And the forcing function for that was the computing system. There's a lot of high-speed computing that goes inside the box to make this thing work. You've got lasers, you've got optics, you've got other components in there, but you need to get all the data processed in real time to get your answers out in real time so that the vehicle can react to it, can use the instrument data to fly. That normally takes a lot of computing power. And we were able to put that onto a board we built here at Langley, to fit inside the box and enable it to shrink. That is pretty much defining the footprint of the box now. So from an engineering perspective, that's probably been our biggest challenge. There are other subsystems in there that we've put a lot of time and effort into making them better, but that's the biggest one from a size perspective.
You know, NASA, as an agency, we develop a lot of cool technology that we use in space, but then a lot of that technology can be used back here on Earth. How could NDL be possibly used in terrestrial applications?
Oh, that's an excellent question. There are a lot of different ways that it has usage right back here. One of them is for autonomous cars. You know, you see that as a up-and-coming, emerging technology. A small version of NDL can be used to track the speed of vehicles very precisely. In theory, you can also track objects around the vehicle also, so you can use it to some degree for hazard avoidance for the vehicle there too. But giving it a very precise vehicle speed is of utmost importance to any autonomous vehicle. It needs to know precisely how fast it's going.
Let's kind of fast forward to next year. Where are you going to be when your NDL system is the descent stage of those two landers, and they're about to land on the lunar surface, and NDL starts working, and it's working beautifully?
The state we'll be in is a state of happiness. That's the state we'll be in. We will be extremely excited, extremely elated that this has worked successfully.
Well, Glenn, thank you so much for taking the time out today to kind of give us the brief history of NDL and the technology. I'm hoping, you know, I know you're gonna do a spot landing on the moon.
Yep.
And I know you're gonna do one on Mars one day.
Yep.
But what I want to see is I want to be able to drive in a car autonomously without driving, knowing that Glenn and Farzine and the team have an instrument on board that's getting me from A to B.
Yeah, excellent. I hope to see that day soon. All right.
Thank you, sir.
Thank you so much, Chris.
Thank you.
I'm very excited about the NDL technology for sure, but this autonomous driving stuff is awesome. And if these guys don't deliver, I'm going to call them personally, see if they'll set up a carpool with me, because I'm ready to avoid the traffic situation, get some productivity on the road.
Hey, but you know, one of the bigger challenges that they're dealing with is getting it down from that suitcase-sized box to even smaller to work inside of vehicles. The technology has already been transferred, and they're working on it actually close to here at Langley where we were.
Well, don't forget, Walt said at the beginning of the show, he talked about splice, because remember, NDL is part of a bigger suite of instruments. So you imagine not only having NDL, but then you have the terrain relative navigation built in, and then you have the hazard avoidance and detection. One day you're going to be driving, and you get some type of obstacle in front of you, it's just going to drive around it, and you don't have to worry about touching the steering wheel.
Perfect.
Let it go on its own.
And you know, it's interesting because that size reduction, they're talking about getting the basic box down to the size of a can of soda. So just think of, there's the lander for Artemis and things like that, but how many other landers that are going to be involved in space exploration that can use that same technology?
Now, we do have some of that same technology in our cars today. We have the side view, the lights that let you know that people are next to you. But that's using cameras. But this is more precise. This is better technology, and hopefully that will be incorporated in other things besides cars and jets and things
Absolutely,
like that.
absolutely. Now, Chris, what do you think about the long-term prospects? We've seen a technology like this, and it's being developed and deployed. What's the future look like using this technology down the road?
I can't wait till we have those 2 CLIPS missions where the NDL will be flying on the landers. Hopefully we'll get successful data, and eventually if we send humans in 2024, they'll be on the human landers. And then eventually as we get on to Mars, this will be a staple for all the technology and all the landers that will be sent out.
So right now we're doing a show on technology that'll be part of that first return to the moon that we'll have in 2024, and then eventually landing on Mars.
Where are you guys going to be in 2024?
You know what? I'll probably be at the Kennedy Space Center doing some programming, doing some live shows with you and you probably. And
hopefully.
Hopefully, yeah.
That's right.
Yeah, and I think we're just going to get those goosebumps that we had for the many milestones that we've witnessed over the years here at NASA. You know, I was alive when man stepped on the moon, but I was very, very young, so I didn't remember it like I remember the shuttle mission. So this is going to be very interesting, and I'm looking forward to it.
You know the difference is going to be?
What's that?
For 2024, he'll have his AARP card.
You know what? That is absolutely right.
But you know, look, it won't matter. What's really interesting is all this technology that we see in development now is going to be riding on the lander, on part of Artemis.
That's right.
Taking the first major step in this process, and we're all going to get to witness it. That is one of the most exciting things that I can think of in terms of NASA in a long, long time, and I'm excited about it, so I really don't care where I'll be.
And knowing this technology right here is a part of Artemis. So,
Artemis. Artemis of Artemis.
Artemis of Artemis.
You're watching NASA Edge.
An inside and outside look
at all things NASA.
Hey, I'm Thomas Serboken, the head of science at NASA, also known as Dr. Z.
And I'm Ellen Stofan, also known as Dr. E. Welcome to another episode of Easy Science. So Thomas, we're here at the Stephen F. Woodvar-Hazy Center in Chantilly, Virginia, at the tail of the Discovery Space Shuttle, because we're celebrating a very special anniversary.
That's right. I just talked to my kid who just started college. He's 18 years old, and astronauts have been in orbit for his entire life. There has been an American in the space station and international partners during the same time. For 20 years, the space station has been inhabited, and what an amazing anniversary of international cooperation. This 6-bedroom building up there, the length of a football field or so, inhabited and doing science.
It's incredible. We feel a really close connection to the International Space Station because about 1/3 of Discovery's missions were helping to construct it. You know, there's modules on the space station from the United States, from Japan, from the European Space Agency, and Russia. And it's such a great example of international cooperation, how even though sometimes we don't get along here on the ground, we can literally go to a higher plane and find a way to cooperate.
That's right. 240 astronauts from 19 countries, nearly 3,000 experiments experiments, and many of them, of course, on the inside. But we have multiple experiments from 3 disciplines hanging from the outside of the space station. I'll pick up one. The structure of neutron stars. The internal structure of that is measured by the NICER experiment. And that is right now taking measurements of X-rays in the sky from the space station.
That's amazing. And you know, my favorite experiment actually has to do with human health. And I think a lot of people don't realize how much research has been done on the International Space Station around human health. You know, almost half of the Apollo astronauts either got an infection in space or got an infection soon after they returned, because what we've discovered is that when you put humans in microgravity, their immune system doesn't function as well. And we've actually done enough experiments on the International Space Station to realize it's the T cell part of your immune response in your body that's being suppressed. Now, that's fascinating because we can use that information to better understand how our immune system works. And obviously right now in the time of COVID, that's really important information.
The other thing that I think about a lot is, and I actually talk to astronauts about it who have been up there for substantial times, is the importance of this experiment called veggie. It sounds just like what it is. It's actually growing plants in space. And what's really exciting is for them, you know, we know psychologically that's really an important part of a livable environment, to have plants, green, that lives there. And frankly also that they can eat. And they love especially some of the very spicy plants that are out there. But a lot of research is being done with these plants to just really learn how, of course, as we prepare for longer duration travel, how we can use that kind of platform to grow food and to have that livable environment.
Yeah, it was funny when I talked to Scott Kelly after he came back from his year in space. He talked about how much growing flowers in space, how much that meant to him in that long year that he was up on the International Space Station. Which reminds me of one of the most important things we use the ISS for that we haven't mentioned. This whole issue of learning to live in space is critical for getting humans not just back to the moon, but onto Mars. It's that 7-month journey to Mars, time on Mars, time back. The International Space Station, we've been using it as a platform to get humans ready, to get our technologies ready to go further out into the solar system.
That's exactly right. There's a number of experiments going on right now on the space station that are really about life support systems that we want to use to go beyond, go to the moon first as part of the Artemis program. And of course, we have one eye on Mars already because, of course, robotically, we're on the way there with Perseverance, but with humans, we want to follow and go there also. And yet, the space station will forever be in the history of that because the technologies were really developed right there.
The ISS has been an incredible platform for student experiments. So every year at any given time up on the ISS, there are experiments going on that were sent up there by students, high school students, even elementary school students at one point, college students. It's an incredible platform to let students get that first understanding of how does science work? How do you design an experiment? How do you get a result and what do you do with it?
That's exactly right. And for me, kind of when I think of the space station, I think of it as a victory of the human spirit and the coming together as the Earth as one, explore as one, both on the human side, but also the scientific side. So I just really want to congratulate the entire team that has been part of that, building it, but also during the entire 20 years, running this highly complex machine internationally. And I look forward to everything we're going to learn in the future as well.
It's an incredible success, and we can't congratulate enough the International Space Station team and all the countries, the European Space Agency, Russia, obviously the US, and Japan, who've been the key core part of the ISS team. Well, I think we're just about out of time. Thank you for joining us for another episode of Easy Science.
Before one small step for man, and one giant leap for mankind. A team of daring space pioneers embarked on a pair of experimental rocket projects to study the Earth and the heavens. With eyes on the sky and the future of space exploration, flight controllers inside NASA's Mercury Control Center watched America's space program take flight. And so here, the story of American space exploration began.
In the late 1950s, the earliest chapters of American space exploration were written along Florida's central Atlantic coast. Later known as the Mission Control Center, NASA's Mercury Control Center was the United States' first mission control for both unmanned and manned space programs. The Mercury Control Center controlled the flights of 3 different vehicles from 3 different seaside launch pads at the Cape. The MCC housed the program's critical launch equipment. Inside the unassuming 30,000 square foot building known to NASA as Building 1385, flight controllers monitored and controlled the Project Mercury launches and the first 3 flights of the Gemini program. The Mercury Gemini program set the stage for the highly technical challenges and accomplishments later executed by NASA Kennedy Space Center.
The Mercury program was absolutely essential to all of our space programs that followed. And the main reason being, it was the proof of the pudding that we could launch into space, we could put a man in there, we could preserve him throughout a mission, we could bring him back safely, and from there, Mercury led into Gemini, going into the Apollo program where we went to the moon.
Florida's mild climate, vast undeveloped land surrounding the Cape, and its proximity to water made it a good choice for launching rockets. And so the Mercury Control Center was designed by the Army Corps of Engineers and built in stages on Cape Canaveral Air Force Station between 1956 and 1963. The modest-looking building faced east toward the ocean, though thick vegetation hid it from view. The MCC had an inset floor and a flat roof. The exterior was designed with a pair of light metal swing doors that open onto covered entrances. Later, the famous NASA logo graced a west-facing exterior wall. Floodlights and speakers were placed along the upper roof edge. Project Mercury began in 1958, 1 week after NASA was enacted, and 3 days before the one-year anniversary of the Soviets' launch of Sputnik.
To steal from Dickens, it was the best of times and the worst of times for the space program. Because, of course, the Russians had put up the first satellite. We had put up a satellite on January 31st of 1958, and the space race was on. Before that time, the missile race was on, and the Soviet Union was rattling their rockets at the United States, and it was a very, very tough time for our nation. So now we were in a space race at the same time, and it appeared once again we were behind.
I would have to say nothing was more exciting than working on the Mercury program because we were doing things for the first time. It was new.
The project's goals were straightforward: orbit a manned spacecraft around Earth, investigate the pilot's ability to function in space, and to recover both the pilot and the spacecraft safely. The flight control room was added to the existing building beginning in 1959 for the upcoming Mercury flights. The upgrade included a viewing area that was built by Bell Telephone Incorporated. A second addition, along the west elevation, provided additional space for support equipment. The flight control room occupied just 10% of the entire building. Christopher Kraft would be the very first flight director, and he was key in the development of the flight control operations and the first flight control team. Chris gave final launch approval. His console was equipped with a black and white monitor, and he had access to every communication circuit, called loops.
But in the final analysis, it had to be this gentleman right here, Chris Kraft, as flight director, running the entire show, and that's what made it work. Chris was an amazing person. He's the only, I'm a communicator, and he's the only person I ever saw that could listen and understand 8 intercom nets simultaneously. I always tease him about that, but that's just he's the only person I know that could do that.
So the combination of the two, between guys on the ground and a crew in space, really was a phenomenal thing in its time. I think we were able to get a lot done, more done than had we not had a control center.
We had the Mercury Control Center right there, right adjacent to the press site, actually. And Chris Kraft was the flight director. Walt Williams was the operations director. And you had a number of other key people who grew up in that program and carried us all the way to the moon as far as flight control was concerned. They had a fantastic worldwide map in there because they were wanted to cover the orbital flights that would follow on the Mercury Atlas.
The MCC was part of the Spaceflight Tracking and Data Network. The tracking network provided communication between the capsule and mission control with an impressive system of ships on 3 oceans and 18 ground stations on 3 continents. As part of this worldwide network of tracking stations, a 2-dimensional world map and 2 large projector boards dominated the front wall of the flight control room. The map used a series of circles to pinpoint tracking stations. To keep continuous track of the Mercury spacecraft, a mini-spacecraft model suspended by wires traced its orbit. The projector boards were used to display flight measurements plotted by sliding beads. Trend charts displayed the astronauts' condition. Goddard Space Flight Center in Greenbelt, Maryland was the link between the remote tracking stations and the MCC. As Project Mercury took shape, so too did the first astronaut corps. Leroy Gordon Cooper, Virgil Gus Grissom, Alan Shepard, Walter Wally Schirra, Donald Deke Slayton, Scott Carpenter, and John Glenn became known as the Mercury 7. They were in training as teams prepared for the upcoming flights. Inaugural operations inside the MCC supported the first Mercury Redstone launch attempt. The MR-1 launch on November 21, 1960 from Launch Pad 6 was classified unsuccessful, but proved many of the systems designed for the vehicle and capsule worked. MR-1A successfully launched a few weeks later on December 19, 1960. The same spacecraft was used. About 6 months later, astronaut Alan Shepard made history with his suborbital ballistic flight on May 5, 1961.
So this was a very significant flight because the country needed this. The whole free world needed this flight at this time.
A Mercury Redstone rocket, MR-3, known as Freedom 7, lifted off from Launch Complex 5-6 at 9:34 a.m. Eastern Time. It was the first manned flight controlled by teams inside the MCC, and it lasted 15 minutes.
It was a beautiful, beautiful May morning. And I was in charge also of the telephone, the intercom service for the control center. And I was also in charge of the air-to-ground. So I had a fairly busy time during all of the launches. But obviously there was an air of excitement in the control center on that first manned flight that you couldn't duplicate anywhere in the world.
That very first flight on that Mercury Redstone, I mean, going up into space and coming back down, even though you didn't orbit the Earth, that set the stage for everything else that we've done.
As the command center, the MCC had 8 primary functions: to direct all aspects of the capsule's flight, monitor the health of the astronaut and the system status of the capsule, make decisions to abort a mission, determine the proper procedures following an abort procedure, command the re-entry of the capsule, keep the astronauts and all the tracking stations informed of the mission's progress, coordinate and maintain the flow of communication between all tracking stations, and inform the recovery forces when the capsule would re-enter the atmosphere. It would take 14 flight controllers to meet these mission objectives. The first critical row of flight control seats was coined the trench. One of those important positions was the capsule communicator, or CAPCOM position, one held only by an astronaut.
I think the Capcom today is very much the same as it was back during the early Mercury days. It's that point of contact with the crew. It provides the crew perspective to the control team. Yeah, very similar.
Public interest in the space program and the astronauts grew as Project Mercury realized much success.
Because the beaches were loaded. The program was pretty small. It was only about 350, 400 people, and it was real excitement. The cities around here were growing. The center was really on its way.
News of the Mercury missions was in the newspapers and on TV.
I've had the pleasure of covering every launch of American astronauts from Cape Canaveral, Florida.
Shorty Powers was the first public information officer for NASA. He was the voice of mission control.
We had a red light that would come on our desk, and that red light was a signal that Mercury Control would have a report in 30 seconds.
Some employees at the Cape were just as excited about the astronauts and the missions as the public.
I met all of the original 7 astronauts because they would come into the ready room. Well, they were excited like everyone else, and everything was new to them. And they would all come through because each one was interested, of course. It wouldn't just one come through, they all would come through.
The Mercury Atlas and Mercury Redstone vehicles flew 26 missions as part of Project Mercury. 6 of those were manned flights. The first orbital flight for the Mercury program was MA6.
Roger, backup clock is started.
Astronaut John Glenn performed it on February 20th, 1962. Astronaut Scott Carpenter followed Glenn's successful mission with his own orbit of the Earth later that year.
Climbing into that spacecraft and sitting on the top of the rocket was something we had simulated time and time again. So, in a certain sense, it was just another day at the office, except this time you realized that it was for real.
MA9 was the last flight of Project Mercury, piloted by Gordon Cooper on May 15, 1963, in his spacecraft named Faith 7. He was the last American to orbit the Earth solo. The mission lasted 1 day, 10 hours, 19 minutes, and 49 seconds.
I named my spacecraft Faith 7 for 3 reasons. 1, because of a belief in God and country. 2, because of a loyalty to organization, to the 2 organizations actually, which I belong. And 3, because of a confidence in the entire space team.
The Mercury program was ending, and America's second human spaceflight program was soon to begin in support of one very clear mission.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Bridging the gap between Mercury and Apollo was the Gemini program. Following the Mercury program, Gemini subjected astronauts to long-duration flights in support of the upcoming Apollo moon missions. Gemini accomplished 10 manned missions and 2 unmanned, each on a Titan II launch vehicle from Launch Complex 19. 2 astronauts flew in the capsule, which is how it got its moniker, Gemini, or Twin. Renovations to the MCC were completed in 1962 and in 1963 in support of the Gemini missions. An addition wrapped around the east, north, and most of the west and south sides of the MCC. New areas included space for flight control briefings, data analysis, and room for a new Gemini spacecraft trainer. The old trend charts on either side of the world map were replaced by rear projection screens. The world map displayed new tracking stations, and one clock above the map changed to estimated liftoff time. A desk for a public affairs officer was also added, along with a pair of consoles on the left side of the room facing inward for the Support Control Coordinator and the Display Coordinator. After the conclusion of Gus Grissom and John Young's flight of Gemini 3 in March 1965, NASA transferred mission control to Houston, Texas, where it still resides today. After mission control functions were relocated to Houston, Texas, the Mercury Control Center provided backup for the initial launch and the trajectory for the remaining Gemini missions. In 1967, the MCC became a tour stop for guests visiting NASA's Kennedy Space Center Visitor Complex. A bus tour provided the public an opportunity to look through the glass windows of the viewing room and see where the first chapters of American space history were written. It was a popular attraction from 1967 through 1995. In the late 90s, the building began to show signs of aging. In an effort to preserve what remained inside the deteriorating structure, NASA removed the artifacts inside. Later, a plan was developed to create an authentic MCC flight control room exhibit at the KSC Visitor Complex.
The opportunity for relocating this amazing room full of history was to offer it to many, many more people. Accessibility to the actual facility was becoming more and more challenging, and it allowed for the consoles throughout the room to be displayed and preserved. Had they been left in the building all those years, they would be in terrible condition right now.
The exhibit is inside an 8,500 square foot building dedicated to early space exploration.
One piece at a time, we carefully removed it, brought it over. So what you see here is a duplication of the actual MCC, the Mission Control Center, with the screens, the consoles, the flooring, the finishes, and of course the tracking board. The consoles themselves are completely authentic. The tracking map is completely authentic.
Guests get a memorable and authentic experience.
I think it's an amazing opportunity for our guests to look through the glass and step back in time and honor the heroic first years of our space program.
The MCC was designated by the National Park Service as a contributing structure to a National Historic Landmark District in 1984. The district consists of 7 other contributing properties: launch complexes 5, 6, 13, 14, 19, 26, and 34. NASA determined the Mercury Control Center was no longer needed for NASA missions and had deteriorated beyond repair. Final artifact preservation efforts began in 2009. The Mercury Control Center controlled the flights of 3 vehicles from 3 launch pads during its years of service. In March 2010, heavy equipment operated by NASA contractors leveled the concrete block and metal building.
You know, it's a transition, but we have to be energy efficient. We have to prepare for the future. We got to prepare for going beyond low Earth orbit and doing bigger and better things. And this is all part of the process as we grow and change here at the Kennedy Space Center. We will never forget our heritage. It's crucial to us. History is important.
Locked, and we are good to send that command. We have 31 minutes and 32 seconds for our support. Go for status buffer dump.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
The Webb telescope will be groundbreaking because it has capabilities that are different than the Hubble Space Telescope.
We have equipment that is so much more powerful than anything we've ever had before that it's almost impossible to tell what we will discover.
Hubble's accomplishments include something called the deep fields, looking out into space and collecting light, sometimes for many days. These deep fields have revealed visually to us a universe absolutely teeming with galaxies, hundreds of billions of galaxies.
One of the neat things about the ultra deep field, and one of the things that made it so unique was how long it took us to take that image. There's an exposure time that's expressed, I think it's 11.2 days. There's a very, very long exposure time. But probably what's more important is how many orbits it took us to do that. 400 orbits of Hubble data to take that image. You only get 15 orbits a day. To take 400 orbits and say, we're going to observe this one spot in the sky for 400 orbits. And the really unique thing about that was they picked a spot where there wasn't anything. They looked and they said, there's absolutely nothing here. And they said, you want to spend 400 Hubble orbits looking at nothing? And they said, yes, because we want to see what it can see. And I think the results from the science, I mean, it was amazing. What they saw was spectacular.
Hubble had spent 2 weeks taking pictures of empty places in the sky, and they saw they weren't empty at all. They were thousands and thousands of galaxies.
We were amazed how many galaxies we've found, and we continue to go back to that portion of the sky to increase that visibility.
The Hubble Space Telescope is an outstanding time machine. It's incredibly important for our studies with the Hubble Space Telescope to realize that when we're looking at a galaxy, we're seeing it as it was millions of years ago, sometimes billions of years ago. It's taken that long for the light to get to us.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
What Hubble has revealed is that the universe has in fact changed over these billions of years of time. The early galaxies, the very distant ones as we see them, are simple. Sometimes they're messy looking, they're small, they haven't had time yet to form that grand spiral structure. Over time, we see galaxies actually merging with other galaxies and growing bigger and bigger, and those mergers can look like train wrecks in our Hubble images.
These very, very deep exposures that Hubble has been able to take, we have seen right to the edge of the universe, 13.5 billion years. When Hubble was first designed and envisioned, it was never thought it could actually see that far out. But because of the advances in the instruments that we've been able to put up on the telescope, and also the cleverness of the scientists, they've come up with very interesting observing scenarios, doing these really deep exposures where we just sit there for orbit after orbit after orbit, gathering the photons. We've been able to push Hubble out very, very far.
As Hubble looks out into these fields of galaxies, we sometimes see clusters of galaxies. These are galaxies that are held nearby each other by their mutual gravity. These clusters are massive conglomerations. There's so much mass that they have an actual observable impact on space-time itself. Einstein predicted that mass distorts space, but we didn't realize we could actually see the effects of that. But with Hubble, we have been able to see distortions in space around clusters of galaxies. The way we see that is when light from a background galaxy travels through that cluster of galaxies or around it due to this gravitational lensing effect. The lensing also magnifies that background galaxy, so if we look in some of these distorted arcs, we can see more detail than we would ever have been able to see without gravitational lensing, nature's boost.
There are observations where we're explicitly looking for the lensing, and they're getting science out of that just otherwise would just not be doable. Hubble has really taken that to the next level. It's doing large amounts of astrophysics that it's just never been able to do before.
Some of what we're doing with Hubble is to prepare for the new James Webb Telescope, which we anticipate launching in 2021, which will be able to see farther into the infrared part of the electromagnetic spectrum. That enables us to see some galaxies that are difficult for Hubble to see because they're so far away that their light is traveling through us through expanding space and gets stretched out into redder wavelengths, often far into the infrared part of the spectrum, even sometimes beyond what Hubble is able to detect well. The Webb telescope will give us more information about some of those very distant galaxies.
The James Webb Space Telescope is the follow-on telescope after the Great Hubble Telescope. It extends the discoveries of Hubble into the infrared spectrum region. We think that the first objects that grew out of the Big Bang material probably happened in about 100 million years after that start. And we think the Webb telescope can pick them up. They're rare, they're hard to find, but they should be there. The farthest we've been able to see with the Hubble telescope goes back about 800 million years after the expansion began. So we think we get much closer to the first objects with the Webb telescope.
Hubble gives information that the Webb telescope cannot give about visible and ultraviolet emission from things in the universe. And when we have all that information coming in at the same time, it's like a banquet of scientific return.
Now when we get the complete picture of every wavelength you can possibly see from ultraviolet to infrared, we hope to have the story of the growth of the first galaxies from the primordial material. So that will be a huge accomplishment that depends on both pieces of equipment, the Hubble telescope and the James Webb telescope working together.
So astronomers are very excited about this probability that we'll have both the Hubble Space Telescope and the Webb telescope operating at the same time for quite a few years. That will give us an abundance of new understanding about the universe. And already right now with Hubble, we're doing preparatory observations for the Webb telescope. We're using Hubble to do things, for example, like surveying distant galaxies to find out which ones would be prime targets for the Webb telescope. In fact, scientists around the world are proposing observations with Hubble right now specifically to help us learn information that will be useful for making the best use of the Webb telescope as soon as it's launched and gets going in its science observations.
I think the Hubble telescope has been the most productive science instrument ever built. In astronomy, there's what we knew before Hubble, and now there's what we know after Hubble. They're so different. Of course, Hubble has now had a life of 30 years, so it's had a long time to make this revolution happen. So it's not all at once. It's a gradual revolution, but it's still a huge revolution. Technology has changed dramatically over the 30 years of life of the Hubble telescope. So you couldn't even have imagined when the Hubble was launched that we would have the wonderful cameras and spectrometers that we buy today. We figured out how to send astronauts, we trained the astronauts, we figured out what instruments could be put in, we figured out how to repair everything that went wrong on the Hubble, and it's still alive. It's today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it didn't have to be that way, but they made it happen.
Attention! NASA television programming on Galaxy 13 is moving from transponder 11 to transponder 15. The transmission modulation format is now DVB-S2 8PSK. This move is in line with the Federal Communications Commission's initiative to free up C-band bandwidth on domestic satellites in support of future 5G terrestrial communications efforts. Transponder 11 and 15 are both active during this transition. Distribution of NASA TV programming on Transponder 11 will end on August 29, 2022. For more information, go to nasa.gov/NASATV.
have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
Hello, and welcome to another episode of NASA Science Live, an opportunity for you to interact with NASA experts and have your questions answered live on air. I'm your host, Tahira Allen, and today we are joining you live from NASA's Goddard Space Flight Center in Greenbelt, Maryland. We will be taking your questions about Webb's historic images all throughout today's show, live on air. For those of you tuning in on social media, you can use the hashtag UnfoldTheUniverse to submit questions or drop your questions directly into the comment box wherever you're watching this stream. This week, the James Webb Space Telescope released its first full-color images and data. And this is just the beginning. As the world's most powerful space telescope, it will examine every phase of cosmic history, from the first luminous glows after the Big Bang to the formation of galaxies, stars, planets, and the evolution of our own solar system. This is a huge moment, marking a new way to see the universe beyond where we have ever been, beyond time itself. Let's take a moment to pull back the curtains and see what Webb has revealed. This first image of a galaxy cluster takes us back 4.6 billion years, giving the deepest and sharpest infrared image of the distant universe to date. This graph, the most detailed of its kind, shows the distinct signature of water in the atmosphere surrounding a hot gas giant planet that is orbiting a distant sunlight star hundreds of light years away. In this image of the Carina Nebula, Webb peers through cosmic dust, revealing previously invisible areas of star birth. Covering about 1/5 of the moon's diameter, this is Webb's largest image to date, showcasing in rare detail a group of interacting galaxies known as Stephan's Quintet. And some stars save the best for last. Webb captured a dying star's final performance, sending out rings of gas and dust for thousands of years in all directions. So now that we have seen these incredible images, let's talk to our experts. I'm joined today by Dr. Alex Lockwood, Webb Project Scientist, and Dr. Nestor Espinoza, Webb Astronomer, both from the Space Telescope Science Institute. Thank you both so much for being with us.
Thanks for having us.
Thanks to hear.
So, the big day is here. We've seen the images, we have the first data. Nestor, I'm going to start with you as our astronomer. Can you talk through what Webb's new images show us that we weren't able to see before?
Well, Webb is revealing a universe to which we were a little bit, it's invisible for us, right? It's looking in eyes that we don't have, in colors of the light that we are not able to grasp. But right now, thanks to this beautiful machine, we're able to see the birth of stars in ways we've not explored before. You know, galaxies far, far away, and even distant exoplanets with impressive detail. So, you know, I'm beyond stoked to be here talking with you about this.
Yeah, absolutely. And you mentioned seeing in colors that our eyes can't see. Webb has this ability. What's so great about that? Like, what do those colors show us about the universe?
Right, depending on the physical process that you're looking at, it can give you a ton of information. For instance, let's look, my expertise is in exoplanets, so of course I'm going to go back there. Yeah. And for exoplanets, the infrared holds the hidden molecules that are the most important for us. When you hear water, when you hear carbon dioxide, when you hear methane, all those molecules are hidden in the infrared, and that's why we have to go there. That's why I'm so excited to see all this flow of data through these images that we can explore together.
Absolutely. And so we have this clear view. We know that the instruments are working. Alex, as the project scientist, can you shine light on how Webb will take humanity's knowledge of the universe to the next level?
Well, it's really complementary to what we've seen with a lot of the telescopes, especially Hubble. Hubble does visible wavelengths and infrared, and James Webb does infrared. And it's kind of like if you look at the human body. We can see a body, we see people every day, but you go to the doctor's office and you get an x-ray and you can see your bones, you can see what's inside someone. And it's very different than what you see when you're looking at the person, but it tells you a lot more information, and it's complementary. It's the same thing. James Webb it's not an X-ray telescope, it's an infrared telescope, but it's the same idea that it gives us a completely different but very informational view of things that we've already seen with Hubble and things that we have yet to see.
Amazing. And so it's my understanding too, this is just the start for Webb. So these are just the first images and the first showcasing of its capabilities. So Alex or Nestor, can y'all give us an idea of what images and data we can expect in the first year of science?
Yeah, absolutely. There are lots of programs that are scheduled from astronomers across the world. I think there's over 40 countries that people have gotten data that they're going to get data from. And we're going to see more images like the deep field that we saw yesterday. People are going to study that, but fields like that for even longer to find even more distant galaxies. Lots of time to do that. In fact, I think that program is running as we speak. A program like that. We're going to look at more exoplanets, which Nestor can tell you all about. And we're going to look at star-forming regions, understand star birth and star death, like one of the images that we saw of the Southern Ring. Really, Webb spans the gamut of anything astronomical, and we have all of that planned in the first year. It's really, really great depth.
Yeah, if I might add, the most exciting to me, at least as an exoplanet person.
Yeah.
Webb is the first observatory that will allow us to explore worlds as small as ours. And these observations have already happened, some of them actually. And they're going to be explored by scientists starting tomorrow. And we're going to start learning about these worlds outside our solar system for the first time with exquisite detail. I don't know what we will see. We have some idea, of course, but the universe keeps us surprising us. And that's what I'm most excited about, the unexpected.
That is amazing. And so it wasn't the WASP exoplanet that we characterized the atmosphere. That was light years away, wasn't that?
It was 1,000 light years away. It's very, very far away. But even though it's so far away, Webb has such a huge mirror and such precise instruments that we can see, water features that you're seeing right now with exquisite details. I don't even have to show you a model. You can see the wiggles going around. Each of those wiggles is water vapor in the atmosphere of this exoplanet 1,000 light years away. Imagine what we can do with this.
No, seriously, that's why I'm getting so excited. It's crazy to think about and just to wonder what is going to come next. This is amazing. This is so exciting. And we have so many questions coming in online. So I'm going to take a pause and we'll take some questions from our viewers. As a reminder to those tuning in, you can submit questions for our experts on today's show by using the hashtag #UnfoldTheUniverse on social media or by dropping your question directly into the comment stream wherever you're watching from. So, our first question is from Charlie on Twitter, who asks, does anyone know if Webb has the ability to view objects within our own galaxy?
Yes, definitely. Well, a lot of Webb's bread and butter is distant galaxies outside our own Milky Way. Most of the star-forming regions and planetary nebula like we saw yesterday, and the exoplanets, all the exoplanets that we can study are actually within our own galaxy. We can see very far because of Webb's big mirror and sensitive instruments, but the closer we are, the more detail we can have. So something like this beautiful nebula that you're seeing right now, that's within our own galaxy, and we can see a lot more details and see inside the nebula to see what's going on.
So we can see within our own galaxy. Can we see within our own solar system?
Yes, we can. We have observations in the first year, as we were talking, to look at objects from Mars all the way out to the Kuiper Belt in our own solar system. Yeah.
I mean, that's amazing. That's really exciting to think about. It's going far. It's going close to home. It's going to be great. And so let's move on to Nick from Facebook, who asks, can the JWST be pointed towards an exoplanet and get a clear image of it? Nestor?
Well, actually, part of the observations that are going to be made, it can get what we call a direct image, which is really like a little blob in a plot, so you won't be able to see these artistic representations that you typically see from these exoplanets. But we can get direct light from some very young, hot, and distant exoplanets out there. So there's some modes. In particular, there's one mode that it's called a coronagraph, which is like, when you're in the street and there's too much light and you put your fingers on top so you don't get, too much light on top. Mm-hmm. That's exactly what we're doing with the star that the planet orbits. So we try to block it with a little needle, basically, which we have some ways of doing it on board. And we're able to see like a little dot going around, and that's the planet. So yes, there will be some observations of that with Webb, which is quite amazing on its own.
Yeah, and what does the coronagraph tell us?
Well, the coronagraph actually tries to remove the star, because the whole point, and this is very interesting to think about, we're able to get light from the farthest away galaxies, right? So very, very faint things. People always ask like, well, how can you not get an image from a planet? They're closer, right? The problem is the star. The stars are so bright that you cannot just see like the faint point of what is the planet right on top of it. So you have to remove it somehow, and these coronagraphs just remove the light from the star, so you can have a pristine look at the planet. It's a little dot.
Okay, cool. That's so interesting. And so Claire on Twitter asks, how does JWST know where to zoom in to capture the images?
That's a good question, and that is actually decided by astronomers worldwide. Every year there's a process of selecting the targets, very rigorous. Lots of astronomers get together and look at the proposals without names on them, so they're unbiased, and they say what's the best science for Webb to do. And then once those targets get chosen, then we put them into our calculators on Webb, and we point Webb. But where it looks specifically at any given time is based on the science target, and those are proposed by astronomers across the world.
Nice. And isn't Webb just very efficient? I know we were talking before that it's really kind of making it a little easy on astronomers right now. Could any of y'all talk to that?
Maybe, yeah, I can jump into that. I mean, the way in which you get from the data to the results, it's incredibly fast. This is a story that we both were part of within producing this very first images. Like the analysis of the exoplanet, in one day we have like one spectrum already. So in one day, these things, with previous instruments, they took like years, like tens of years even for some instruments. But now Webb, it's so stable, it produces data so pristine that you're able to extract information right away from it. So that speaks of its efficiency at observing how the data is reduced, etc. So it's gonna open up, it lowers the bar so people can jump and do science on their own, much faster, much quicker, and much more efficiently. So
yeah, and I'll add that deep field image that we saw with all the galaxies in it, that was taken in less than 12 hours with Webb. And a similar image that wasn't as sensitive took over 100 hours with Hubble. And so you're talking about 10 times faster to get even more data. That's really good efficiency.
I mean, I think it's safe to say that it was worth the wait.
Yes.
Webb is doing some great things. So moving on, we have Holger on YouTube who asks, what interesting observation is planned of objects within our solar system?
Yeah, that's a really good question. So we are going to look at Just like we're studying with exoplanets, the atmospheres, we're going to look at the atmospheres of planets within our own solar system, the ice giants and the gas giants. There's a lot of beautiful cloud structure in Jupiter and Saturn that we're going to study, as well as the moons of those planets to understand the entire system more. And again, look at these molecules that Nestor was referring to, methane, carbon dioxide, that are very strong in infrared wavelengths.
So I actually have a really good follow-up question to that. On Parith Viraj on YouTube asks how these photos are useful for space scientists and other scientific communities. So while we do get this data, I guess, could you talk a little bit about how it might be applied?
Sure, yeah. So these images actually, whenever you're seeing these beautiful colors on these images, you're reading physical processes happening in them. And this is the most amazing thing that we have, there's teams behind it that actually maximize the information content, so to speak, on these images. So, some colors here, like in these beautiful galaxies that you're seeing here, like this yellowish, there's some dust, some star formation, and then with this whitish color, you see the cores of these galaxies. So those are different physical processes happening in these images. Here in this beautiful nebula, you're seeing this gas that is very, very, very hot, very ionized, the blue one in the center. That's telling you something, that there's energy from the central star, that it's blowing that, giving energy to that gas, and you can see it right away. So this is not only beautiful images, this is like beautiful physical processes that you can understand better with this crisp, beautiful, colorful representations that we're seeing in these beautiful images.
And does this kind of play a part in helping us understand how our planet was formed?
Absolutely. One of the really incredible things to me about Webb is that it's going to study everything from the birth of stars and the planets that form around them, all the way to fully formed exoplanets. And so when you're interested in, why does the Earth have water, you have to go back to the source material, which is really all of the molecular cloud that it started from. And how did it end up at Earth and not anywhere else, for example, in our solar system. So we're going to look at the entire evolution of these really interesting molecules, and maybe we find another Earth-like planet. But if not, we'll be able to see water in the original cloud, and then it condensing out onto grains, and then it finding its way to a planet. Webb studies every moment of that, and it's really going to answer questions about our own Earth, about how unique or common we are.
So I'm glad you said that. Erez on Facebook actually has a great follow-up for you, Nestor. Why is finding water vapor important? Why is water vapor important to Earth?
Well, water vapor important in general in these exoplanets. It's super interesting because it tells you something about how these planets formed. Actually, the amount of water that you extract from this plot that you were seeing, I can tell you, what's the amount of water in this planet, and that tells me, exactly what Alex was just saying, how water got there. And how it got there depends on where the planet formed. So I can track the formation of the planet back to the whole history. That's on these giant planets, but in the small planets like ours, water tells you, also how it's delivered, but water here speaks typically of life, right? That's the thing that motivates most of these speak about water on rocky worlds. So it can go from all the little details to how it formed to to life itself. So water is extremely important. That's how we know how life emerges over here. So that pins the interest on this beautiful molecule. Yeah.
I mean, is this even real? It's like Webb does so much. It is just so amazing. And Amin on Facebook asks, how does Webb actually work to capture images?
You want to go? It's a complex process because these detectors, for instance, just starting, how you detect this light. You're used to these cameras that you have in your cell phones, right? This pixelization, etc. Well, the detectors on Webb, for instance, they have to be very, very special because infrared light you have to know how to capture it. Not anything can capture that, right? So just starting from there, it's extremely complex. Then if you go to all the way up to where the light is coming, the optical path that it has to go through the telescope, it reflects on different mirrors inside to get to your instruments, and dispersing the light in order to make sense out of it. All of that, it sounds like a complicated process, but we made it happen. And we made it happen, and I have to make this point here, thanks to the international collaboration behind Webb, like NASA, ESA, CSA, the Canadian Space Agency, the European Space Agency, this confluence of different minds to make this complex observatory happen. That's how it works. So yeah, it's a complex process all the way, and even interpreting that data now, creating the beautiful colors that you are seeing, that's also a challenge on its own. How do you maximize the information in these images? So there's all the way from technological advances to us humans interpreting these images. It's a whole path that is very, very complex. That's why we were laughing with Alex, because it's like, it's such a complicated thing, but we make it happen as humans. And I think that's a beautiful thing to celebrate.
Absolutely, and wasn't so much of the technology on Webb actually new? It was literally created for the telescope. People had to make this stuff from scratch, right?
Yeah, we had never put something into space that was this big. We had to fold it. We had to make lightweight enough material that we could actually get it up in a rocket, even though it was so big. The back plane that holds the mirrors, the sun shield material, and a lot of the detectors themselves, all new technology.
Wow. And the 6-month commissioning period, it's incredible. Anyways, so Aurel on Twitch asks, how do Webb's images not get blocked by the stars in our galaxy? Nestor, I think you mentioned a little bit on that, but if you could expand.
Yeah, no, some stars photobomb our galaxy images, right? And you can actually see it in some of the images that were released. So that happens sometimes. But the important bit, and that's why the first deep field image, one of the important bits on this, you can see a star there, like the brightest dot there. That's a star. But you can see that why don't we capture so many stars as well is because this is such a tiny image. I mean, that's impressive. It was said when the person was showing up this, that it is like as small as a grain of sand, projected on the sky. So that speaks wonders of what you can get out of this. But yes, stars do photobomb our galaxy images, but we know how to deal with them.
Mm-hmm, mm-hmm. And the closest star, we built a giant sun shield to block that light.
Yeah.
So
the sun, yes, of course.
That's funny. So Emma on Twitter asks, hey NASA, I was wondering what's coming next. What are the next targets for Webb, and how often will we be surprised with new images and data?
That's a good question. Well, I can tell you that during this week, they have been looking at some of the deepest galaxy fields and some of the rockiest planets. So really, in the past couple of days, they have spanned the gamut of science and distance. And you can anticipate new data and images definitely within the next few weeks. Mm-hmm. And then I would say that every month at least Webb is going to surprise us. There are already astronomers out there who have taken data that was released today and are starting to analyze them and figure out the amazing scientific results. And so you won't have to wait long. I can say that.
Okay. I mean, that's great. That sounds good to me. I'm sure with everybody else. And so we've waited long enough. So you said that Webb's targets have spanned the gamut, spanned all across the universe. Has it captured anything in our solar system already?
Yes. So actually, during the 6-month commissioning process, there was an image taken of Jupiter to test some of the modes to make sure that it wasn't too bright, to make sure that we could track Jupiter as it moves across the sky, because objects in our solar system move much faster relative to distant things. And so those were successful images, and you can see them here. Successful doesn't even say anything because they're beautiful. So as we said, we're going to study objects in our solar system, and for Jupiter, one of the very interesting things is the clouds and understanding the cloud structure. which pops out clearly in one of these images. And so this data itself just came out today, as all of the data from the past 6 months was released publicly today.
Great. And so we have Marcia on Facebook who asks, there are more than 5,000 known exoplanets, and being able to provide spectroscopy at the level of Webb is outstanding. How many of those exoplanets are scheduled for observation?
Oh, that's a good question. In the first year, I remember the list was in the several tens, at least within now. And that there's a beautiful picture that was made by Nicole Colon from NASA, showing the whole span. It covers the span from rocky planets. In fact, one of them, perhaps one of the most exciting one, TRAPPIST-1 system. We can speak more about that later, but that one hosts some planets that might be in the habitable zone, and this system was already the observations are already there. They're already taken by Webb. They cover all the range from rocky planets to giant planets, hot, cold, you name it. All the diversity is out there in this first year, so I cannot wait to see what comes out of this.
I mean, your energy is like, I can feel it right now, so I'm very excited about this as well. Overview Effect on Twitter asks, what was the exposure time of the released images, and how does the Webb's deep field compare to Hubble's ultra deep field?
Yeah, so each of these images, it depends on the image, but yeah, you can see the beautiful comparison with Hubble's image of the same field and Webb's. And as I mentioned before, this image of Webb took, I think it was total 12 hours, and the Hubble field took days. So really a very large difference for time that it took. For the other images that were released yesterday, they were all between 6 and 12 hours apiece, depending on the image. And yeah, Webb is just as powerful as Hubble, and I think these images really show that they're complementary, and Webb has the beautiful resolution and added detail.
I mean, it's amazing. It's like going to the eye doctor and getting your glasses updated. You can see clearly now, and this is incredible. So, Nestor, I've got a good one for you. Wild Dogs OG on Twitch asks, I wonder why NASA looked at WASP 96b first instead of Proxima Centauri or Alpha Centauri or even TRAPPIST-1.
That's an excellent question. First of all, the Proxima and Alpha, they're too close, they're too bright, but we'll find ways to figure those one out.
Okay.
But WASP 96b, it's a very, very interesting planet on its own. So the story goes that when we look at other exoplanets with Hubble, whenever we look at a hot giant exoplanet, we find clouds. And that's no surprise if you, like in retrospective, that was no surprise, because when you look at the solar system, all giant planets have clouds. But then this one, the features that Hubble was seeing, and also ground-based telescopes were seeing, are so distinct that there was this belief that maybe it didn't have clouds. And that was very weird. Like I was personally weirded out by this. So, NASA made the excellent selection to go with this planet to figure out, what we will see with Webb size. And guess what we found with Webb size? Clouds. Yes, we found like some very, very distinct signatures of clouds. So if you look in detail, with a detail as precise as what Webb Ice presents to us, you actually found things that you believed that they were not there before. And that was exactly the case with WASP 96b. So I think it teaches us a lesson. And I tell you, we have people from the scientists right now trying to figure out all the little details, trying to model the data from the picture that we released. So it's exciting on its own. It's a very, very exciting system.
It is exciting too to just hear that we have learned something that we didn't expect in just the first observation. Again, This is just the start, and so that is incredible to think about. So we have Tara Blakeham on Twitch who asks, what were your thoughts and reactions when you saw the colorized pictures for the first time? What did that feel like?
When the first image was taken of the Carina Nebula, which is that beautiful landscape that we saw yesterday, the first image, just one color of the image, was available. We immediately downloaded it and just looked at the raw data. And I literally teared up because there was so much structure just in one color, and you can see it in the image. The structure equals scientific potential, because those details are where you extract all the nuance in the story and the science. And I teared up. I could not believe how good Webb was. Better than expected. It's been really emotional.
I can imagine. Nestor?
Yeah, no, I had the same. And the beautiful thing was seeing the process, you know? The process of yes, you get, you know, color by color, and you start adding. It's like making a painting of the universe, right? And you're right there, sitting in this big table with these beautiful images just being made, and being these, you know, amazing human beings next to you, being able to share that with the world later. It was a whole experience. So it was a very, you know, people typically think that we scientists, like, you know, are very, very smart. This was a very human experience of sharing, of amazing each other, of, you know, just peering into the universe with these pictures. It was amazing. Yeah.
We sat in a room literally every day for the past month, a group of about 30 of us, scientists and artists, and looked at these data as they came down. And it was, I mean, it was a privilege. It was amazing. And yeah, as Nestor said, you know, it was a team effort, and the human element of trying to do the best by this mission, by, you know, humanity, to really wow people. And I mean, Webb brought it.
Yeah, absolutely. I mean, that's the best way to put it. So, Alex, Nestor, we will be back with you in just a bit to answer some more questions from our viewers. For those of you tuning in, keep sending your questions online. You can submit them using the hashtag #UnfoldTheUniverse on social media, or by dropping your question directly into the comment box wherever you're watching from. The Webb Space Telescope is just starting its science and still has so much to reveal about our universe. The newly released images have given us a never-before-seen view of the cosmos and reminded us how science and art are so beautifully woven together. As the telescope continues to peer into the great beyond, what do you think Webb will see? Show us by creating art. You can sing, you can dance, you can write, you can paint. In this case, the universe is literally the limit. Share a photo or video of you and your creation using the hashtag #UnfoldTheUniverse for a chance to be shared on NASA's website or social media channels. Need some inspiration? Let's take a look.
I think the sun, the stars, the galaxies, the solar system and other systems are in the sky. And the stars are made of sunlight. There is heat and solar radiation and other elements.
Este telescopio para tomar muchas fotos y bonitas.
All right, we are back with Dr. Alex Lockwood, Webb Project Scientist, and Dr. Nestor Espinoza, Webb Astronomer, to keep taking some more of your questions online. If you're just tuning in with us, be sure to submit your questions using the hashtag UnfoldTheUniverse on social media or by dropping your question directly into the comment box wherever you're watching this stream. Yesterday, communities around the world were hosting special events for Webb's image release, and we received a video question from one student named Olivia, who is part of the Girl Scout troop of Tropical Florida. Let's take a look.
Hi, my name is Olivia Galvan, and I'm from Miami, Florida. And my question is, will the James Webb Telescope give us more information about the Earth's climate change?
Great question, Olivia. So, Nestor, Alex, what can Webb tell us about Earth's climate change?
Well, this is an excellent question, Olivia. Thank you very much. Well, the reality is that Webb has this promise, of being able to explore distant exoplanet atmospheres, even for the ones of planets that might host habitable conditions, maybe even similar to Earth. So that allows us actually to start peering into the diversity of atmospheres out there. And that actually teaches us, where maybe our atmosphere might end. And therefore, or how many other types of atmospheres end. And that can actually, inflow into our understanding of our own climate change here on Earth. Mm-hmm. Alex, other thoughts?
Yeah, well, to me, climate change is a really big question and a big challenge for humanity to take on. And that's actually just like Webb. 20 years ago, people had big, audacious questions about the universe, and then we built exactly the perfect, incredible tool to answer those. And it was an international collaboration. That's the only way that it was possible. And so I think, tackling Webb and tackling climate change are similarly audacious challenges, and we've proven we can do it. So I really think that gives us hope for the question of what we can do for climate change.
I mean, absolutely. Seeing what Webb has done, that leaves me hopeful. Yeah. So, that sounds great. Our next question is from Tesla Hype on Twitter, who asks, what might Webb teach us about dark matter or dark energy?
Well, these detailed images that you were just seeing about galaxies, there's some of them for which you can see such exquisite details as to, where certain populations of stars are hidden, or, even some of the dynamics you will be able to see about these galaxies. That's the key for investigating dark matter, for instance. Dark matter is one of the parts that dominate the whole dynamics in these galaxies, and therefore it will definitely tell us new clues about how dark matter is spread through different types of galaxies. There's even, the hypothesis that maybe some galaxies might not have a ton of dark matter, for instance, but those are very, very faint. But then Webb has such huge mirror that it can actually peer into those with very, very, enough detail to tell you, oh yes, maybe it doesn't have. So all these questions, yes, it will enable us to answer them. And in terms of dark energy, this strange thing that it's making on the universe to not only expand, but expanding in an accelerated fashion, like every second it's expanding faster. Because Webb can reach out to the most distant galaxies, it can actually teach us a ton about how this expansion happens at different positions, at different times even. So yes, definitely, it will allow us to peer into details that we have not had the chance to before, for sure. Yeah.
So one thing that I think is really cool is how we tend to use different telescopes. We use data from multiple different telescopes to get an even bigger picture of the universe. So will Webb be complementary to any of the other space telescopes that are already out there, or that might be coming up in the future?
Alex, you want to take this?
Absolutely. You can already put Hubble and Webb images side by side, and you see that there's additional information that you can get from both of those images. And in terms of studying the scales of the universe and dark matter and dark energy that we were just talking about, the LIGO mission, the LIGO telescope that measures gravitational waves, it has found some incredible pairs of rotating neutron stars that helps us understand Einstein's original equations. Webb has the ability for when a unique phenomenon like that happens, Webb has the ability to stop what it's doing and go look at that to provide additional information. And there's actually a system between telescopes where they can alert each other to say, there's something really important and timely going on in the universe. Let's look at it together to get added information. And so Webb will be part of that as well.
So telescopes can like phone a friend, and oh my gosh, that's amazing. That is a fun fact. So Wait 1 Minute on Twitter asks, how do scientists separate stars from galaxies in such pictures?
Well, the structure tells you a lot about that. First of all, the fact that galaxies are, we have a name for them, like, diffuse sources or not. I can't remember actually now the word, but we know which sources are like galaxies or more diffuse, and while stars are very, very pointy points in the images. There's a point though, in which, especially for the faintest stars, in which it gets like kind of tough to separate between them just from an image. So you have to go and get more data. There's a point in which it gets challenging, but for most of them, we have a pretty good idea on how to do that.
I actually have a great follow-up to that. So Aerononis on Twitch asks, how do you convert the data into such colorful photos?
Want to take this?
Sure. The data come down, as ones and zeros. But basically, what you do is you focus on one color of light at a time, and on your infrared detector, you say how much light is being collected on any given point on the detector. And so you actually have like a spatial map for where the light is coming in. And the more light you get, the brighter it is in that one wavelength and that one color. And then we take many color pictures, individual wavelengths, and then add them together to make color images.
It's a process on its own. It's that whole art. We have experts in-house back at Space Telescope that did all this, and seeing this work unfold, unfold the universe, was like magnificent. How we humans can make this happen in these beautiful images. It's a whole process that I loved. Yeah.
It is, and I'm glad that you said that, and you alluded to it earlier about how Webb is truly an international mission. Didn't over